Somewhere deep in the black tapestry of space, past the stars and galaxies we can see, lurk things that are darker than darkness. We've come to accept black holes as the ultimate end, places where matter collapses, time distorts, and light vanishes. But what if we've been wrong? What if some of those terrifying voids aren't black holes at all, but something even stranger? Something with no singularity, no true event horizon, no bottomless pit, but instead, a hollow sphere of dark energy encased in an alien shell? Welcome to the world of gravastars. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Gravastars, short for gravitational vacuum stars, are among the most bizarre concepts in modern astrophysics. These theoretical objects are not only weirder than black holes, in many ways, they are more terrifying. Because while a black hole represents a catastrophic collapse of matter, a gravastar represents something far more mysterious: the victory of the vacuum over gravity, the dominance of an antiforce that repels instead of pulls, and a cosmic object that mimics a black hole perfectly, yet hides a completely different truth underneath. The gravastar is a cosmic trickster, a shape-shifting shadow that might wear the skin of a black hole, but underneath, it holds a different kind of horror. At its core lies not matter, not energy as we know it, but a patch of nothingness, a vacuum dominated by negative pressure. This vacuum, instead of allowing a singularity to form, pushes outward, halting gravitational collapse in its tracks. Around that vacuum, a paper-thin shell of exotic matter forms the structure's body, so dense and so strange, it would tear apart anything trying to touch it. The idea sounds like science fiction, and in many ways, it is stranger than fiction. But gravastars weren't dreamed up by novelists. They were proposed by physicists, trying to resolve some of the deepest inconsistencies in our understanding of black holes. Because for all their majestic terror, black holes are problematic. They seem to erase information. They predict singularities where the laws of physics break down. And they don't play nicely with quantum mechanics. Gravastars are one attempt to patch these holes in our cosmic fabric. And in doing so, they open up a Pandora's box of new questions. Could we ever tell a gravastar from a black hole? Could we detect their mergers and gravitational wave signals? Could they be linked to dark energy, the very force pushing the universe apart? Might they even be gateways, relics, or something more alien still? As we journey through this video, we'll peel back the layers of the gravastar idea, from the origin of the theory to its implications for quantum gravity, time dilation, and the ultimate fate of stars. We'll explore whether they could explain mysterious observations in our universe, whether they might be stable, and whether they could even be used for technologies we haven't begun to imagine. This is more than just a look at an obscure physics paper. This is a journey to the edge of science, to the very limits of our understanding, where gravity, space, and time are stretched and twisted into forms we can barely comprehend. Whether gravastars are real or not, they force us to ask deeper questions. What is a vacuum, really? What happens at the end of a star's life? And could the universe be hiding secrets inside objects we thought we understood? So buckle in. The black hole might not be the final boss of the cosmos. Something else might be lurking in its shadow, something just as dark, but infinitely weirder. To understand the enigma of gravastars, we first need to grasp what they are and how they fit into the cosmic hierarchy. A gravastar, or gravitational vacuum star, is a purely theoretical object, one that challenges our most accepted assumptions about the fate of collapsing stars. When a massive star exhausts its fuel, the standard narrative tells us it implodes under its own gravity, compressing into a point of infinite density known as a singularity, surrounded by an event horizon. This is the defining characteristic of a black hole. But a gravastar proposes a radical alternative. What if, at the brink of collapse, the laws of physics intervene and create not a black hole, but something altogether different? Instead of forming a singularity, the star's collapsing core transitions into an exotic state, an ultra-dense shell enclosing a vacuum filled with dark energy, or a form of negative pressure. This vacuum isn't emptiness in the usual sense. It's an active force, repelling rather than attracting, pushing outward as gravity pushes inward. The result is an equilibrium that halts the collapse just before a singularity can form. What remains is a sphere that's deceptively similar to a black hole on the outside but fundamentally alien on the inside. Imagine a hollow ball, but not one made of empty space. Inside this sphere is a patch of vacuum unlike the one between the stars. This is a vacuum charged with energy, a vacuum that resists being crushed. Around it, hugging the vacuum like a tightly drawn skin, is a shell of exotic matter. This matter isn't like the atoms and particles we're familiar with. It's theorized to violate what physicists call the energy conditions, meaning it could have negative mass or other bizarre properties. This shell provides the structure, preventing the vacuum from expanding or collapsing, while the vacuum prevents the shell from caving in. From far away, this object looks indistinguishable from a black hole. It has mass. It bends light. It curves space-time. But look closer, if that were even possible, and you might not find an event horizon. You might not find a singularity. You might not even find matter in the traditional sense. What you would see, hypothetically, is an object that plays by different rules, a cosmic body where the laws of gravity and quantum theory are in a kind of strange truce, a compromise that defies both complete collapse and traditional stability. This is the gravastar, not a black hole, not a neutron star, but a third possibility. A liminal object. A cosmic boundary marker. It sits on the edge between collapse and expansion, between the known and the unknown, between Einstein's general relativity and the mysterious framework of quantum gravity. It's not just a new type of star, it's a new type of idea. One that forces us to reconsider what the universe allows, and what it might be hiding behind the veil of gravity. The notion of gravastars didn't emerge from science fiction or idle speculation. It came from a serious attempt to reconcile the sharp contradictions between general relativity and quantum mechanics. In 2001, physicists Paul Mazur and Emil Motola introduced a groundbreaking idea that would challenge one of the most sacred icons of modern physics, the black hole. Their paper, Gravitational Vacuum Condensate Stars, an alternative to black holes, proposed a startling possibility, that perhaps black holes, as traditionally understood, never actually form. That instead, something else happens at the very edge of gravitational collapse. Mazur and Motola's idea was born from dissatisfaction with some fundamental problems that plague black hole theory. Chief among them, the singularity and the information paradox. Singularities, the theoretical points of infinite density and zero volume inside black holes, are where general relativity breaks down entirely. Physics as we know it cannot describe what goes on at a singularity. It's like asking what's south of the South Pole. It's a mathematical end of the road, and yet the equations of general relativity demand it. That's deeply unsettling. Worse still, black holes appear to swallow information. According to quantum mechanics, information about a system should never be destroyed. It can change form, become scrambled, but it must always be preserved. Yet in the standard black hole model, anything that crosses the event horizon is lost to the universe. If the black hole evaporates over time via Hawking radiation, that information seems to vanish with it, violating the fundamental laws of quantum theory. Mazur and Motola saw an opportunity to bypass these dilemmas by suggesting a new endpoint for collapsing stars, one that didn't require an event horizon or a singularity. They imagined a kind of gravitational phase transition, not unlike the way water freezes into ice, but on a cosmic scale. As the star collapses, instead of continuing unchecked into a singularity, the extreme pressures cause the vacuum inside to undergo a quantum transformation. A new state of matter emerges, a gravitational vacuum condensate. This new state generates negative pressure, a kind of repulsive force that halts the collapse and stabilizes the structure. In their model, the result is a gravastar, a central region of this vacuum energy, surrounded by a thin, rigid shell of ultra-dense matter. The interior, dominated by the repulsive effects of negative pressure, pushes outward just as gravity pulls inward. This delicate balance replaces the singularity with something smoother, something finite, and potentially something testable. Their gravastar had no true event horizon, just an extremely steep gravitational gradient that, from a distance, would appear nearly indistinguishable from one. What made the proposal especially intriguing was how it mirrored concepts already appearing in cosmology. Dark energy, the mysterious force accelerating the expansion of the universe, also exhibits negative pressure. If dark energy dominates the cosmos at large scales, could a similar vacuum-dominated structure exist at small scales, inside collapsed stars? Mazur and Motola essentially asked, what if we put a little piece of the universe's dark energy inside a star? Their theory was bold, controversial, and difficult to test, but it offered a possible way to keep both general relativity and quantum mechanics intact without discarding either. It introduced a new class of objects into the astrophysical zoo, with a structure more complex and fascinating than black holes, and a behavior that could potentially be observed, at least indirectly, through its gravitational effects or merger signals. Though the gravastar remains hypothetical to this day, the Mazur-Motola proposal sparked a wave of research. Physicists began to ask, could such an object really exist? Would it be stable? Could we distinguish it from a black hole observationally? And most of all, could it solve the problems that black holes create? In retrospect, 2001 wasn't just the year we imagined monoliths and space odysseys. It was the year we reimagined what might lie at the heart of the universe's darkest objects. Mazur and Motola opened a door that still hasn't been shut, and beyond it lies a world where gravity doesn't end in destruction, but in transformation. Black holes are among the most elegant and terrifying predictions of Einstein's general relativity. Their mathematical structure is simple yet profound. Take enough mass, compress it into a small enough region, and it will warp spacetime so severely that nothing, not even light, can escape. Yet for all their theoretical beauty and observational confirmation, black holes come with deep, unsettling problems. These problems aren't just philosophical, they're existential for physics itself. And it's these issues that motivated physicists to search for alternatives like gravastars. The most glaring problem is the singularity. At the heart of a black hole, general relativity predicts a point of infinite density and zero volume, a place where the curvature of spacetime becomes infinite, and the known laws of physics break down entirely. It's not just that we don't know what happens there, it's that our theories literally cannot say. Any time a theory produces infinities, physicists get uncomfortable. It usually means the theory has reached its limit, like trying to divide by zero. Singularities are where predictability ends, where space and time as we understand them cease to have meaning. They are mathematical abysses that suggest something is wrong or incomplete in our models. But singularities aren't the only problem. There's also the infamous black hole information paradox. In classical general relativity, anything that crosses the event horizon of a black hole is gone forever. It can't escape. Its details, what it was, what it carried, what interactions it had, are lost to the outside universe. However, quantum mechanics insists on a very different principle, unitarity. This means that information about a physical system is never truly lost. Even if something changes form, even if it gets scattered or spread out, the underlying information must always be preserved. This clash comes to a head when we consider black hole evaporation, a process predicted by Stephen Hawking in the 1970s. According to Hawking's calculations, black holes emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over vast periods of time, this causes the black hole to slowly lose mass and eventually vanish. But the radiation is purely thermal. It carries no information about what fell into the black hole. If the black hole evaporates completely, the information about its contents seems to disappear with it, violating the rules of quantum theory. This isn't just a technical issue, it threatens the foundation of modern physics. If black holes truly destroy information, then quantum mechanics, our most successful and precisely tested theory, would need to be rewritten. That's an outcome few physicists are willing to accept. So the question becomes, is there a way to describe the endpoint of gravitational collapse without creating a singularity or violating the principles of quantum information? That's where gravastars enter the scene. Gravastars were proposed not as random replacements, but as solutions to these paradoxes. By eliminating the singularity and avoiding a true event horizon, gravastars potentially offer a way to preserve information and stay within the bounds of quantum mechanics. In a gravastar, matter never collapses to a point of infinite density. Instead, it halts at a critical threshold, forming a vacuum-dominated core surrounded by a shell. There's no region where space and time break down, and potentially no place where information becomes irretrievably lost. Even the causal structure of a gravastar, the way cause and effect unfold in its vicinity, could be different. In black holes, the event horizon is a one-way surface. Once you pass it, you can never come back. But in some gravastar models, there is no such irreversible boundary. Light and matter might be trapped temporarily or severely delayed, but not necessarily lost forever. Some researchers have even suggested that if gravastars can emit modified Hawking-like radiation from their surface instead of a true event horizon, then the emitted particles could carry information in a way that preserves quantum consistency. In this view, gravastars don't just patch over the holes in black hole theory. They offer a full rewrite of the final act in a collapsing star's life. This pursuit also aligns with a broader trend in physics, trying to unify general relativity, which governs the very large, with quantum mechanics, which governs the very small. Black holes sit at the intersection of these domains, and right now, the two theories give incompatible answers about what happens there. Any model, like the gravastar, that can serve as a bridge between them, becomes a tantalizing possibility. So physicists began to ask, not out of rebellion but out of necessity, what if black holes are not the end of the story? What if the universe has a more consistent, quantum-friendly alternative, one that doesn't destroy information, doesn't produce infinities, and doesn't force us to abandon the very rules that govern particles, atoms, and fields? That's why gravastars matter. Not because they're easy. Not because they're proven. But because the alternative, the breakdown of physics at its most extreme, might be even harder to accept. At first glance, a gravastar might seem like a simple concept, a collapsed star that didn't become a black hole. But peel back its structure, layer by layer, and what emerges is an object far more complex than any ordinary star or even a black hole. The gravastar is a cosmic onion of contradictions, with each layer playing a crucial role in maintaining its bizarre, delicate balance between gravity and anti-gravity. It isn't just a shell or a void, it's a dynamic, three-tiered system where known physics is pushed to its absolute limits. The first and most fundamental part of a gravastar lies at its core, an inner region composed not of regular matter, not of compressed atoms, but of pure vacuum. This isn't an empty void in the traditional sense, but a specialized vacuum with an exotic property, negative pressure. It's theorized to be filled with dark energy, the same mysterious force believed to drive the accelerated expansion of the universe. But within the gravastar, this vacuum energy plays a much more localized and potent role. It exerts an outward push, counterbalancing the overwhelming inward pull of gravity from the collapsing mass. This negative pressure, often modeled using the equation of state, where pressure is the negative of energy density, behaves like a form of repulsive gravity. It resists compression and acts like a built-in cosmological force field. Rather than continuing to collapse into a singularity, the matter that once formed the star gets arrested at the brink of gravitational implosion, forming this peculiar vacuum-dominated region. In a way, it's like placing a piece of the expanding universe inside the heart of a dying star. Encasing this strange vacuum is the second layer, a thin shell of exotic matter. This layer is critical. Without it, the internal pressure would cause the structure to explode outward. Think of it like a cosmic membrane stretched tight around a balloon of dark energy. This shell is thought to be incredibly thin compared to the overall size of the object, but it contains all the mass that gives the gravastar its gravitational pull. It's not just a boundary, it's the physical manifestation of the star's remnant material, transformed under extreme conditions into a form that likely violates the known energy conditions of classical physics. In standard matter, energy density is always positive, and gravity always attracts. But exotic matter, at least in theory, can have negative energy density, enabling strange gravitational effects such as repulsion, stabilization of wormholes, or the prevention of singularity formation. The shell's role is twofold. it contains the vacuum within, and it gives the gravastar its external gravitational footprint. To an outside observer, the gravastar's mass would appear concentrated in this shell, while the inner vacuum contributes no net gravitational pull due to its unique properties. Finally, some models also suggest a third layer, an outer crust or transition zone. This region, if it exists, might contain highly compressed forms of matter just before the exotic shell begins. It's not as fundamentally important as the inner vacuum or the exotic shell, but it could serve as the last remnant of what was once the collapsing star's outer layers. This crust may help mediate interactions between the gravastar and the environment around it, such as infalling matter, radiation pressure, or particle emissions. Together, these three components form a finely tuned structure: a void pushing outward, a shell pushing inward, and possibly a crust interfacing with space. The result is an object that doesn't collapse further and doesn't evaporate in the usual sense, but instead sits in a kind of gravitational limbo, sustained by an internal balance of opposing forces. From the outside, a gravastar might appear to have a strong gravitational field, similar to a black hole of equal mass. Light passing near it would still bend. Objects orbiting it would behave much the same. But unlike a black hole, whose defining feature is its event horizon, a surface from which nothing can escape, the gravastar's surface is a physical structure. There's no singularity inside, and possibly no true horizon. Just an ultra-dense skin of alien matter wrapped around a core of nothingness. This tripartite structure, vacuum core, exotic shell, and potential crust, sets the gravastar apart from anything else in the universe. It's a kind of cosmic sculpture, held together not by brute force, but by the most delicate balancing act in nature. At the center of a gravastar lies one of its most radical features, a region not filled with matter, not even with ordinary vacuum, but with a highly energetic and mysterious substance that resists compression, dark energy. This isn't just empty space, it's a vacuum with power, a vacuum with pressure. And it's this core that redefines the very idea of gravitational collapse. In most astronomical objects, the core is where density increases, pressure builds, and gravitational force intensifies. But in a gravastar, this pattern is reversed. Instead of a dense core made of collapsed matter, the interior is composed entirely of a gravitational vacuum condensate, a region with a constant energy density and a pressure that's exactly negative that energy. This is not a metaphor. In physics terms, this relationship is expressed through an equation of state, where is pressure and is energy density. It's the same signature associated with the cosmological constant, the driving force behind the universe's accelerated expansion. In simpler terms, imagine a bubble of energy that pushes outward instead of collapsing inward. In normal stars, gravity tries to crush the core while thermal and radiation pressure push outward to maintain balance. But in a gravastar, the core isn't filled with particles generating outward pressure. The vacuum itself is the pressure. There's no radiation, no particles bouncing around, only the geometry of spacetime and the field of negative pressure it contains. This is where dark energy comes in. Dark energy is the name we give to the unknown force causing galaxies to accelerate away from each other at ever-increasing speeds. It makes up about 68% of the total energy of the universe, yet we have no direct understanding of what it is. What we do know is that it has this curious trait: it behaves like a pressure that repels rather than attracts. In the context of the universe, it stretches space. In the context of a gravastar, it prevents collapse. This substitution of a singularity for a region of dark energy is perhaps the gravastar's most elegant move. It avoids the problems of infinite density and zero volume by placing a kind of cosmological repeller at the center of the object. The collapsing star never reaches the critical point of no return. Instead, its core becomes a kind of high-energy vacuum, not one devoid of substance, but one filled with a smooth, constant energy that shapes spacetime in subtle and powerful ways. It's important to understand that this vacuum isn't simply nothing. It's a structured nothing, a field with defined energy characteristics. In quantum field theory, even empty space isn't truly empty. It seethes with fluctuations, virtual particles, and potential. The vacuum inside a gravastar might be a kind of lowest energy state, like a Bose-Einstein condensate of gravitational fields, an idea Maser and Mottola originally proposed. This condensate would have coherence, structure, and resistance to change. It wouldn't radiate, wouldn't collapse, and wouldn't allow particles to exist within it. The result is a gravitational interior that acts more like an anti-gravity bubble. Instead of sucking everything in, it pushes back, but it does so with incredible subtlety, just enough to hold the gravastar in equilibrium. There's no burning, no fusion, no accretion. The energy is static yet immense, and its only purpose is to resist further collapse. What makes this truly fascinating is how this interior affects the fabric of spacetime. The curvature inside the gravastar is radically different from that inside a black hole. Instead of warping spacetime toward a point of infinite curvature, the core creates a kind of smooth, rounded geometry, a hollow, perhaps spherical zone where the gravitational field flattens out. To an outside observer, this curvature would be hidden behind the dense shell, but its effects would shape the gravastar's behavior in gravitational fields, light propagation, and perhaps even the emission of quantum radiation. If dark energy is indeed the substance of the gravastar's core, then this structure doesn't just challenge the idea of a black hole, it unites cosmology and astrophysics in a deeply profound way. The same force that is expanding the universe might also be stabilizing the remnants of collapsed stars. The infinitely large and the infinitesimally small might be connected by the same mysterious ingredient. And perhaps, if we can understand how such a vacuum forms in the heart of a dying star, we'll come closer to understanding what dark energy really is, not just in distant galaxies, but at the very edges of life and death in the universe. Surrounding the bizarre dark energy-filled core of a gravastar is its most structurally crucial and exotic feature, a thin shell composed of ultra-dense matter unlike anything known in conventional physics. This shell is not just a boundary, it's the keystone that holds the entire system together. Without it, the repulsive pressure of the vacuum inside would burst outward, destabilizing the structure. With it, the gravastar achieves an exquisite balance between collapse and expansion, creating a star that neither dies nor evaporates, but lingers in a state of quantum equilibrium. The shell is theorized to be made of exotic matter, a type of material that violates the known energy conditions in general relativity. In particular, it may have negative energy density or negative pressure, features that are forbidden by all known forms of normal matter. Ordinary matter, like gas, plasma, neutrons, or even the strange matter found inside neutron stars, cannot sustain the kind of pressures and properties required for this shell. Instead, the shell is proposed to consist of something deeply alien, potentially born out of a quantum phase transition in spacetime itself. This shell is thought to be incredibly thin, possibly only a few Planck lengths in thickness, mere fractions of a billionth of a trillionth of a centimeter, yet it must contain the entire gravitational mass of the gravastar. It's a paradoxical construct, a structure infinitesimally small in thickness, yet astronomically massive in density. All of the object's gravitational influence comes from this razor-thin ring of matter, while the vast interior vacuum contributes no additional pull. To an external observer, the shell's mass curves spacetime exactly as a black hole would. But there's a difference. Inside, there is no singularity, no crushing center, only vacuum. What makes this shell so strange is how it might behave. In some models, the shell could exhibit properties associated with quantum coherence, or even superfluidity, allowing it to maintain structural integrity without friction or dissipation. Others suggest it might act like a domain wall, a kind of boundary between two different vacuum states, like a cosmic version of a soap bubble stretched to its limit. In these scenarios, the shell is not simply matter compressed into a crust, but a membrane that emerges from the very topology of spacetime, possibly held together by quantum fields, strings, or even holographic principles. The shell's job is to maintain equilibrium. On one side, it must counter the outward push of the vacuum core, an internal pressure that would otherwise tear it apart. On the other, it must resist further gravitational collapse, stabilizing just before it would become a true event horizon. This in-between state is critical. The gravastar never fully collapses into a black hole, nor does it explode outward like a failed star. It's a suspended object, frozen at the edge of possibility. Because the shell is so thin, it creates a steep but continuous gradient in the gravitational field. That means, instead of an event horizon, a sudden boundary beyond which nothing returns, the shell acts more like an extreme gravitational slope. Light and particles approaching it may still be trapped or delayed dramatically, giving the illusion of a black hole. But crucially, the shell remains a physical surface, not a metaphysical edge. That opens up profound implications. For example, radiation could, in principle, be reflected or scattered by this shell, allowing some form of information to escape, potentially solving the information paradox without requiring a singularity. Furthermore, the exotic matter comprising this shell might exhibit behaviors forbidden to classical matter. It could interact weakly with normal particles, produce unusual quantum signatures, or even modify the surrounding vacuum state. Some models speculate it could emit subtle types of quantum radiation or gravitational echoes, delays in gravitational wave patterns, that would not be present in standard black hole mergers. The idea of exotic matter isn't entirely new. It's been proposed in other theoretical constructs like wormholes and warp drives, which also require violations of classical energy conditions. In those cases, exotic matter is what prevents collapse and enables strange topologies of spacetime. In gravastars, it serves a similar role, the guardian of structure, the wall between expansion and implosion, the thinnest and densest skin the universe could allow. If gravastars do exist, their shell would be the key to distinguishing them from black holes. Not through direct observation, our telescopes can't yet resolve such minuscule features, but perhaps through their behavior during cosmic collisions, or through slight anomalies in the gravitational waves they emit. In the cosmic masquerade between gravastars and black holes, the shell is the mask, and underneath it, the universe may be hiding one of its most radical tricks. Perhaps the most chilling aspect of a black hole is not its darkness, nor its invisibility, but its singularity, the theoretical point at the center where gravity becomes infinite, density shoots beyond measure, and space-time itself folds in on itself like a crushed sheet of cosmic paper. It's the ultimate breakdown of the known universe, a place where Einstein's equations no longer function, and where quantum theory provides no clear answers. A singularity isn't just a region we don't understand, it's a place where our understanding stops entirely. Gravastars rewrite that ending. Unlike black holes, gravastars do not end in a singularity. In fact, they avoid it altogether, not by magic or mathematical trickery, but by fundamentally changing what happens during gravitational collapse. In the gravastar model, the core of the collapsing star never becomes infinitely dense. Instead, as the inward pressure grows and matter is squeezed tighter, the process is halted just short of catastrophe. Rather than forming a singularity, the matter transitions into a new phase, a gravitational vacuum with negative pressure. Collapse is arrested not by brute force, but by a profound shift in the nature of the core itself. To understand how this works, consider what a singularity truly is. In general relativity, a singularity occurs when the curvature of spacetime becomes infinite, which typically happens when a massive object collapses beyond its Schwarzschild radius, the critical boundary where not even light can escape. But infinite curvature is more than just a math problem. It implies a point of zero volume and infinite energy density, where causality breaks down, time ceases to flow in any meaningful way, and no known law can predict what happens next. Gravastars offer an escape from that abyss. The vacuum core, filled with dark energy, or a gravitational condensate, generates repulsive pressure that halts the collapse before it crosses the threshold into singularity territory. Instead of matter crushing itself into a point, it's transformed into an expansive vacuum region. Spacetime inside this region is smooth and well-behaved. There's no infinite curvature, no divergent energy, and no physical laws being torn apart. Instead of a terminal point, the center of a gravastar is a stable zone of negative pressure, a bubble of vacuum energy that bends spacetime gently outward. In practical terms, this means the gravastar's interior doesn't represent a region of infinite density, but rather zero density, because it's empty of traditional matter. Yet it's far from empty in energy terms. The vacuum inside possesses energy in a different form, one that doesn't curve spacetime into a death spiral, but instead maintains a kind of balance. In effect, the gravistar dodges the singularity not by fighting gravity head-on, but by sidestepping its worst outcome with a phase change of spacetime itself. The implications of avoiding a singularity are enormous. First and foremost, it removes one of the most glaring theoretical inconsistencies in black hole physics. General relativity doesn't predict what happens at a singularity. It only shows that something must happen. This is why physicists believe general relativity, brilliant as it is, must eventually give way to a deeper theory, a theory of quantum gravity that unites the quantum and the cosmic. But gravastars may serve as a placeholder for that theory, offering a model where the rules of quantum field theory can coexist with gravitational collapse, because there's no infinite density region to reconcile. Moreover, without a singularity, a gravistar doesn't destroy information in the same way. While we'll explore that idea more deeply later, the absence of a singularity means there's no ultimate boundary beyond which information must vanish. In a black hole, anything falling past the event horizon is doomed to spiral toward the singularity and be lost forever. In a gravistar, there may be no such endpoint, only a vacuum interior where information could, in theory, be stored or re-emitted in subtle, quantum-consistent ways. It also opens the door to mathematical completeness. A gravistar's internal geometry can be described all the way to its center, without the need for undefined boundary conditions or infinite values. That makes it more attractive to theorists, especially those working on quantum cosmology or holographic models of gravity. In essence, the gravistar removes the most terrifying aspect of a black hole, the physical singularity, and replaces it with something equally strange, but far less pathological. It doesn't offer answers in place of the singularity, but it offers a structure in place of a void. It offers continuity where black holes offer finality. And it invites new ways of thinking about space, time, matter, and energy, not as broken at the center, but transformed. The event horizon is the defining feature of a black hole, a one-way veil draped across the fabric of space-time, beyond which nothing escapes. Cross it, and you are cut off from the rest of the universe forever. No signal, no matter, not even light can claw its way back out. But gravastars rewrite this central idea. They do not have a traditional event horizon. And yet, paradoxically, they can still trap light. They can still mimic the behavior of a black hole so well that even our most sensitive telescopes may not know the difference. In the gravistar model, the ultra-dense shell that surrounds the dark energy core marks the outermost physical boundary. But unlike a black hole's event horizon, this boundary is not a mathematical surface of no return, it's a real, physical structure. A shell of exotic matter, existing at or near the Schwarzschild radius, but not forming an actual horizon. This has enormous implications for how light behaves in its presence. Because of the immense gravity near the shell, space-time is still dramatically curved. Photons traveling near the gravistar can become gravitationally lensed, bent into circular orbits, or caught in long, spiraling trajectories that keep them suspended near the shell's surface. In many respects, the outer edge of a gravistar behaves like an optical trap. To a distant observer, light seems to hover just above the surface, taking eons to escape, if it does at all. This delay is so severe that, practically speaking, light could take longer than the age of the universe to reach an external observer, giving the illusion of total darkness. This phenomenon is called quasi-trapping, and it produces effects astonishingly similar to those of an event horizon. Even though there's no strict point of no return, the light is so gravitationally delayed that it might as well be lost. But the key difference is that, in a gravistar, this light might eventually emerge. In contrast, with a true event horizon, escape is mathematically impossible. Once inside, always inside. The gravistar keeps the door open, if only a crack. This subtle distinction could have profound implications. If light and other forms of information can eventually escape from a gravistar, then the black hole information paradox is no longer paradoxical. Instead of being trapped beyond an inescapable boundary, information might just be delayed, scrambled, distorted, but not destroyed. The gravastar provides a stage for a slower, more complex play of light and gravity, one that could be fully compatible with quantum physics. Furthermore, this absence of an event horizon changes the way a gravastar interacts with its environment. In falling matter, instead of vanishing into nothingness, would crash into the physical shell. This collision might generate energy, shock waves, or radiation, forms of feedback not expected from a black hole, which absorbs everything silently. In theory, this could lead to subtle but detectable differences in the behavior of matter falling into what we think are black holes. The edge of a gravastar also lacks the infinite redshift of a true event horizon. In black holes, light emitted just above the horizon is stretched out, redshifted into invisibility as it climbs out of the gravitational well. But in gravastars, while redshifting still occurs, it's not infinite. There is always some, however minuscule, fraction of light that escapes. This means that a gravastar may be capable of radiating in ways black holes cannot. There's even speculation that echoes in gravitational wave signals could betray the absence of a true event horizon. When two massive objects collide, say, in a merger detected by LIGO or Virgo, the gravitational waves they release might bounce off a solid shell if one or both were gravastars. This would generate tiny echoes or delays in the waveform. Black holes, lacking a surface, would not produce these echoes. Though no conclusive echoes have been found, some studies have reported intriguing anomalies, glimpses, perhaps, of gravastar-like behavior hiding in plain sight. So, while gravastars reject the event horizon, they preserve its optical illusion. They trap light in complex gravitational fields, delay information nearly infinitely, and produce observational signatures nearly identical to a black hole. But beneath the surface, the story is fundamentally different. There's no mathematical cliff, no singularity, no loss of causality, just a shell wrapped around a vacuum, daring the universe to tell the difference. At first glance, gravastars and black holes might seem indistinguishable. Both are incredibly compact, incredibly dark, and bend spacetime so severely that light itself can be trapped in their gravitational grip. In fact, to a distant observer, they would likely look the same, an eerie void against the stars, emitting little to no light, warping the paths of nearby objects and photons. But beneath that veil of similarity lies a gulf of fundamental differences. While black holes and gravastars might mimic each other in outward appearance, their internal structures, physical mechanisms, and philosophical implications are dramatically different. Let's begin with what they have in common. Both are the products of extreme gravitational collapse, and both exhibit very strong gravitational fields. Their gravitational influence on nearby objects, whether it's stars, gas, or light, is dictated by their mass and the geometry of spacetime around them. In general relativity, this is described by the Schwarzschild solution for non-rotating, uncharged bodies. From a mathematical perspective, a gravastar can replicate the Schwarzschild geometry almost perfectly outside its shell. That means orbital patterns, time dilation effects, and gravitational lensing from a distance will all appear nearly identical between the two. But the similarities end there. A black hole has two defining features that a gravastar fundamentally lacks: a singularity at its core and a true event horizon surrounding it. These are not mere details. They are the essence of what makes a black hole a black hole. The singularity represents an endpoint of spacetime, a region of infinite curvature where all known laws break down. The event horizon is the point of no return, beyond which no information, energy, or matter can escape. Once you cross that horizon, your fate is sealed. Gravastars, by contrast, are built to avoid both. Their cores do not collapse into singularities. Instead, the inner region becomes a vacuum filled with dark energy, or a gravitational condensate, exerting negative pressure that halts collapse. This replacement of a singularity with a smooth vacuum region makes the gravastar mathematically well-behaved. There are no infinities, no undefined regions of spacetime, and no breakdown of physical law. Instead of an event horizon, gravastars have a dense physical shell, a thin layer of exotic matter that replaces the abstract mathematical boundary of a black hole. This shell is nearly, but not exactly, at the Schwarzschild radius. It allows gravastars to trap light, and time dilate signals in ways that approximate an event horizon, but without actually forming one. This subtle shift is profound. It means that, in theory, no information is permanently lost. Light and particles might linger near the shell for astronomical timescales, but they could, eventually, escape. Gravastars offer a potential solution to the black hole information paradox, which arises precisely because of the presence of a true event horizon in black holes. There are also differences in how these two objects would interact with infalling matter. In a black hole, anything that crosses the event horizon is simply gone, no reflection, no impact, no trace. But in a gravastar, the shell is a physical surface. Matter slamming into it might produce observable radiation, or even trigger a sort of echo. That could result in signals, gravitational or electromagnetic, that subtly differ from the silent absorption we expect from black holes. From a thermodynamic standpoint, black holes have entropy proportional to the area of their event horizon and emit Hawking radiation due to quantum effects near the horizon. This leads to the eventual evaporation of the black hole over incredibly long timescales. Gravastars, on the other hand, may not emit Hawking radiation in the same way, because they lack the same kind of horizon. If they radiate at all, it would likely be through other mechanisms, possibly related to their shell or interactions between quantum fields near the surface. There's also a fundamental philosophical divergence. Black holes represent a boundary of knowledge, regions we cannot peer into, governed by laws we cannot fully describe. They mark an end point in our understanding of gravity and quantum physics. Gravastars, however, represent a continuation, a bridge, perhaps, between the smooth geometry of Einstein's universe and the probabilistic chaos of quantum theory. They suggest that collapse doesn't have to end in destruction, it might culminate in transformation. In short, black holes are absolute. Once something becomes a black hole, it's sealed off from the rest of the universe. Gravastars, by contrast, are ambiguous. They imitate black holes convincingly but maintain a physical, quantum-respecting structure beneath that facade. They hint that nature might have a way of preserving information, avoiding infinities, and obeying the full suite of physical laws, even in the most extreme environments imaginable. So while the night sky might not tell them apart, and our current instruments may struggle to distinguish one from the other, the difference between a gravastar and a black hole is nothing short of cosmic ideology. One is a wall, the other a window. From afar, a gravastar is one of the greatest cosmic impostors. It walks and talks like a black hole, gravitationally, visually, and even thermodynamically, but it is not one. At least, not in the traditional sense. This raises one of the most critical and exciting questions in modern astrophysics. Can we actually tell the difference between a gravastar and a black hole? Is it even possible, with today's technology, or tomorrow's, to pull back the mask and expose which of these monsters lurks behind the cosmic curtain? At first, the answer might seem discouraging. For an outside observer, the gravitational field of a gravastar can be almost identical to that of a black hole. According to general relativity, the external spacetime of any spherical, non-rotating, uncharged mass is described by the Schwarzschild solution. That means if two objects, one a gravastar and the other a black hole, have the same mass and radius, they will bend light and influence objects in their vicinity in the exact same way. The warping of spacetime, the time dilation, the gravitational lensing, all of it would match. You could orbit either for eternity and never suspect a difference. But the illusion isn't perfect. And this is where things get fascinating. The first way scientists try to distinguish these objects is through gravitational wave astronomy, a field that exploded into life with the groundbreaking detection of gravitational waves by LIGO in 2015. When two massive objects, like black holes or neutron stars, spiral into each other and merge, they produce ripples in spacetime, gravitational waves, that propagate across the cosmos. These waves carry detailed information about the objects involved, their masses, spins, and most intriguingly, their structure. If two black holes merge, the resulting gravitational waveform follows a very specific pattern. There's a chirp as the objects spiral in, increasing in frequency and amplitude. Then comes the merger, a brief but powerful burst of gravitational energy. Finally, there's the ring down, a fading signal as the merged black hole settles into a stable state. Here's where gravastars might reveal their true nature. Some theoretical models suggest that if two gravastars merged, the ring down phase would differ. Why? Because a gravastar has a physical surface, a dense shell. When the merged gravastar settles, gravitational waves could reflect off this shell and bounce back into the surrounding space-time, creating gravitational wave echoes. These echoes would be subtle, delayed repetitions of the main waveform, appearing milliseconds or seconds after the main signal, depending on the object's size and mass. They wouldn't be loud, and detecting them would require extreme precision, but they might be detectable. Several papers have reported tentative evidence of such echoes in LIGO and Virgo data, though the findings remain highly debated. The signals are faint and often buried in noise, but even their possibility opens a path toward distinguishing black holes from gravastars using nothing but spacetime itself. Another avenue is the Event Horizon Telescope, EHT, the network of radio telescopes that produced the first image of a black hole's shadow in 2019. That image showed a bright ring of emission surrounding a dark central region, believed to be the silhouette of the event horizon in the galaxy M87. But a gravastar could, theoretically, produce a very similar image. Why? Because the intense curvature of spacetime near a gravastar's shell can trap light in photon spheres, circular orbits that give rise to a shadow nearly identical to that of a black hole. However, there's one subtle difference. The inner surface of a gravastar is reflective or partially opaque, rather than a sink. That means some of the light or energy that would disappear into a black hole might instead be scattered or delayed in a gravastar. Future improvements to the EHT, or more advanced versions of similar interferometric arrays, could reveal tiny deviations in the photon ring structure, variations in brightness, polarization, or timing that indicate interactions with a shell instead of a true horizon. These deviations wouldn't be obvious. They'd require sub-microarc-second resolution and exquisitely calibrated instruments. But they're theoretically detectable. Another difference might lie in the thermal or electromagnetic emissions from the object. In black holes, infalling matter crosses the event horizon without resistance, vanishing silently. But in gravastars, that matter collides with the shell. This impact could release energy, not in the form of jets or explosions, but as unique thermal signatures, shockwave emissions, or particle cascades. If we could observe the radiation produced as matter strikes the gravastar's shell, we might be able to distinguish it from the smoother, quieter consumption by a black hole. Likewise, X-ray observations could provide subtle clues. Accretion disks, those swirling, superheated rings of matter spiraling into compact objects, behave differently depending on the object they orbit. In black holes, the innermost edge of the accretion disk is governed by the innermost stable circular orbit, ISCO, beyond which matter plunges inward rapidly. If a gravastar has a physical surface just beyond the would-be event horizon, then accreting matter may not plunge but instead collide or pile up near the shell. This could lead to spectral differences in the emitted X-rays, shifts in energy distributions, timing variations, or thermal echoes. Advanced X-ray observatories, such as NASA's NICER or ESA's future Athena mission, might eventually detect such differences. In particular, quasi-periodic oscillations QPOs, repeating patterns in X-ray brightness, could behave differently for gravastars than black holes due to the presence of a surface rather than a horizon. There's also the intriguing possibility of detecting thermal radiation from the shell itself. In a gravastar, the shell may slowly radiate energy due to quantum processes or residual heat from its formation. In contrast, black holes only emit Hawking radiation, which is far too faint to detect with current instruments, especially for stellar mass or supermassive black holes. If a gravastar emits any measurable thermal or quantum radiation, even at extremely low levels, it might provide a detectable signature. Still, all of this depends on technological progress. Most of the effects described, gravitational wave echoes, photon ring brightness, X-ray variations, are at the very edge of current observational capability. And even then, none of them provide conclusive evidence alone. For now, gravastars remain observationally indistinguishable from black holes. But that's changing. As gravitational wave detectors grow more sensitive, as telescopes grow sharper, and as our models of exotic compact objects become more refined, we may start to uncover anomalies, subtle inconsistencies in waveforms, odd radiation signatures, faint echoes in space-time. Any one of them could be a clue. And when pieced together, they might form a picture not of a black hole, but of something stranger, a star made of vacuum, wrapped in exotic matter, reflecting light and energy where a black hole would erase it. So the answer to the question, can we tell the difference, is not yet. But perhaps soon. The universe may have already shown us gravastars. We just haven't realized it. To understand how a gravistar might form, we must journey into the heart of cosmic death, the moment when a massive star ends its life in a spectacular collapse. Traditionally, this collapse results in either a neutron star or, if the mass is great enough, a black hole. But what if there's a third possibility? A hidden path that deflects the death spiral of gravity at the final moment, forming something even stranger, a gravastar. The birth of such an object, if real, would not only redefine how we think about stellar evolution but could also force us to confront deeper truths about the structure of spacetime itself. In the traditional picture, once a massive star, say, at least 20 to 30 times the mass of the Sun, exhausts its nuclear fuel, there's nothing left to support it against gravity. The core collapses. Electrons and protons are crushed into neutrons. The outer layers explode outward as a supernova, while the core shrinks into an incredibly compact object. If it's small enough, a neutron star forms, an object so dense that a teaspoon of it would weigh more than a mountain. But if the collapsing core exceeds about 2 to 3 solar masses, the Tolman, Oppenheimer, Volkoff limit, even neutron degeneracy pressure can't resist the pull of gravity. According to classical theory, the result is inevitable, a black hole. But what if that collapse doesn't go all the way? In the gravastar hypothesis, just before the core passes through the Schwarzschild radius, the threshold for forming a black hole, something unusual happens. Instead of forming a singularity and event horizon, the conditions inside the collapsing core cause a phase transition in the very nature of spacetime. Matter is no longer the dominant factor. The gravitational field itself becomes unstable in the classical sense, and a new state of vacuum emerges, one filled with dark energy, or a gravitational condensate. This vacuum state isn't just empty, it exerts a negative pressure, an inward resistance to compression. It begins to push back against the imploding material. As gravity tries to crush the collapsing star inward, the vacuum pushes outward, setting up a perfect balance. Matter is no longer free-falling toward a singularity. It's hovering at the edge of ultimate collapse, frozen by a counterpressure from within. This is the central mechanism of gravastar formation, gravitational collapse halted by a transition to a vacuum with negative pressure. The vacuum core effectively inflates like a bubble, pushing outward even as gravity bears down. Surrounding this vacuum bubble, the matter of the original star is caught in limbo. Instead of compressing into a singularity, it is squeezed into a razor-thin shell, an ultra-dense layer of exotic matter that forms the gravastar's outer structure. But what triggers this phase transition? That's the great mystery. Theoretically, it could be a function of quantum gravity effects that only become significant at extremely high densities. At such scales, spacetime might not be smooth and continuous, as general relativity assumes. Instead, it could be quantized, grainy, fluctuating, and filled with latent energies. In this chaotic quantum froth, new states of vacuum could emerge. Perhaps certain conditions, like temperature, pressure, and gravitational energy, push the collapsing matter past a critical threshold, at which point the vacuum condenses into a new state, much like how water turns to ice under specific conditions. It's analogous, in some speculative way, to the birth of the universe itself. During cosmic inflation, a high-energy vacuum drove exponential expansion, shaping the early universe. A collapsing star might reverse that logic, contracting into a point of such intensity that a local inflationary bubble forms instead of a singularity. In other words, the very act of death in a star might mimic the act of birth in the universe, but on a smaller scale. Some versions of this theory suggest that quantum backreaction could be responsible. As gravity intensifies during collapse, quantum effects, normally negligible, might suddenly explode into relevance. Virtual particles, vacuum fluctuations, and exotic fields could swell into real, tangible energies, creating a feedback loop that halts further collapse. Instead of gravitational force reaching infinity, it finds a limit. That limit becomes the boundary of the gravastar. Others propose that the cosmological constant itself, the energy of the vacuum, plays a role. Perhaps regions of collapsing matter interact with the cosmological vacuum in strange ways. The gravitational field could distort the vacuum energy locally, creating a pocket of dark energy where none existed before. This pocket inflates, forms the gravastar's core, and locks the outer matter into a stable, suspended shell. It's also possible that certain conditions in the progenitor star influence the process. For example, rotation, magnetic fields, or even the presence of dark matter could tweak the collapse dynamics. A rapidly rotating star might distribute its mass unevenly, leading to regions where vacuum pressures emerge more easily. Strong magnetic fields could alter quantum transitions, creating feedback loops that encourage vacuum formation over singularity creation. In rare cases, perhaps 1 in a billion, these conditions might be just right for a gravastar to form. Of course, all of this remains deeply speculative. No one has seen a gravastar being born. But we have seen supernovae that behave strangely, ones that don't produce visible black holes, or where the energy budget seems off. We've detected compact objects that behave oddly, emitting bursts of radiation or gravitational waves that don't fully align with black hole expectations. Could these be infant gravastars? If gravastars do form in nature, it might mean they're not entirely rare, just rarely distinguishable. They could be quietly masquerading as black holes across the universe, hiding behind the veil of observational similarity. And yet, every time a massive star collapses, there could be a fork in the road. Most paths lead to black holes. But one, narrow and precise, might lead to something stranger, a gravitational vacuum star, balanced on the edge of reality, born not in silence but in transformation. To understand the deepest roots of a gravastar, we must leave behind the familiar roads of classical physics and enter the uncertain terrain of quantum gravity, a theoretical frontier where space-time itself becomes granular, probabilistic, and entangled. Unlike black holes, which are solutions born entirely within Einstein's general relativity, gravastars are born from a marriage between gravity and quantum mechanics, two pillars of physics that, even today, resist unification. In this emerging synthesis, gravastars may represent not just exotic possibilities, but critical clues about the true nature of space, time, and the quantum structure of the universe. At the heart of the mystery lies the basic contradiction between general relativity and quantum field theory. General relativity describes gravity as the curvature of space-time caused by mass and energy. It works beautifully on large scales, planets, stars, galaxies, the universe itself. But it breaks down in extreme conditions like those at the center of a black hole or the origin of the Big Bang, where it predicts singularities, points of infinite density and zero volume. In contrast, quantum field theory governs the behavior of particles, fields, and forces on the smallest scales. It has been tested to absurd precision in labs, but it completely ignores gravity. These two theories are fundamentally incompatible at the Planck scale, where both become important. Black holes highlight this conflict in the most violent way. Their interiors, especially near the singularity, are governed by enormous curvature where general relativity cannot be trusted. At the same time, quantum effects near the event horizon, like Hawking radiation, suggest that information may be lost forever, in direct contradiction to the unitarity of quantum mechanics. This is the infamous black hole information paradox, and it has driven physicists to seek a more complete theory, one that merges the curvature of space with the fuzziness of quantum reality. Enter gravastars. These objects propose a resolution not just to singularities, but to the conceptual friction between quantum mechanics and gravity. In this view, a gravastar is not simply a black hole substitute. It is the physical manifestation of what happens when gravitational collapse is modified by quantum gravitational effects, a snapshot of spacetime when the classical theory gives way to something deeper. In the gravastar model, when a massive star begins to collapse, the standard path would be a plunge past the Schwarzschild radius into singularity. But before that happens, quantum effects become dominant. These are not just Hawking's edge-of-horizon corrections, they are core-level, high-energy modifications of the spacetime geometry itself. Instead of forming a singularity, the collapsing matter undergoes a phase transition into a vacuum state, possibly a Bose-Einstein condensate of gravitons or another unknown quantum gravitational field. This isn't ordinary vacuum. It's a gravitational vacuum condensate, a hypothetical state proposed by Maser and Motola, where spacetime behaves as a coherent quantum fluid. In this fluid, the curvature is smooth, the energy is negative, and gravity is repulsive rather than attractive. This is what allows the inner core of a gravastar to resist collapse and hold back the formation of a singularity. Such a core might arise naturally in any theory where spacetime is quantized, not continuous, but made of discrete, indivisible units, much like matter is composed of atoms. In loop quantum gravity, LQG, for example, space is composed of tiny loops of quantum fields. In string theory, the universe's fundamental building blocks are not point particles but vibrating strings, which operate on Planck-length scales. In both of these frameworks, extreme gravitational collapse might trigger the appearance of a quantum spacetime phase, a new state of geometry that doesn't obey classical rules. In some models, this inner quantum core even behaves like a false vacuum, a local minimum of energy that is stable over cosmic timescales, yet inherently different from the true vacuum of empty space. The shell that surrounds the core would then represent a kind of domain wall, the boundary between two quantum vacua. Inside, the exotic condensed phase. Outside, the normal structure of spacetime. The gravastar, in this sense, becomes a topological defect in spacetime, a bubble of new physics sealed off from collapse by the pressure of its own quantum identity. And what about the shell? That razor-thin layer of exotic matter, balanced delicately between inner pressure and outer gravity, may also be a product of quantum gravity. It could consist of exotic fields, perhaps relics of high-energy particle physics, that emerge from vacuum fluctuations at the Planck scale. Some models suggest this shell might exhibit superfluidity, a quantum state with zero viscosity, allowing the gravastar to avoid dissipation and maintain stability. Others propose that the shell could reflect quantum fluctuations or act as a holographic screen, encoding information about the entire object, a nod to the holographic principle, which proposes that all information within a volume of space can be represented on its boundary. Gravastars may also tie into quantum entanglement and space-time emergence. A bold proposal in modern theoretical physics suggests that space-time itself may be a macroscopic illusion, arising from patterns of quantum entanglement among microscopic degrees of freedom. In this view, the gravastar's inner vacuum would be a region where these entanglement patterns change or break down, giving rise to a fundamentally different internal geometry. This would explain why the center of the gravastar doesn't collapse, but instead behaves like a vacuum with negative pressure. It's no longer spacetime, in the usual sense. Another possibility arises from asymptotically safe gravity, a theoretical idea where gravity remains well-defined and predictive even at very high energies due to the existence of an ultraviolet, UV, fixed point. In such a scenario, the behavior of gravity changes dramatically at small scales, smoothing out singularities and preventing infinite densities. Gravastars might be natural endpoints of collapse in this framework, formed when gravitational interactions flow toward the UV-safe fixed point instead of diverging into a singularity. The beauty of the gravastar is that it provides a physical picture for how quantum gravity might manifest, not in unreachable accelerators or abstract thought experiments, but in the cosmos itself. If we can observe even one real gravastar, it may serve as experimental evidence for a quantum theory of gravity, evidence that the universe does not permit singularities, that event horizons are not absolute, and that space and time themselves can change their character under extreme conditions. In essence, gravastars are test beds for quantum gravity. They stand as possible products of a universe where Einstein's curvature meets Heisenberg's uncertainty, where the granular nature of the cosmos prevents infinities, and where collapse is not finality but transformation. In a universe ruled by both the geometric logic of relativity and the probabilistic dance of the quantum, gravastars may be the natural and necessary middle ground. The elegance of the gravastar concept lies not just in its ability to avoid singularities and bypass event horizons, but in the sheer plausibility of its design, at least on paper. The equations balance. The space-time geometry can be smooth. The vacuum core pushes outward with negative pressure, and the shell resists collapse with exotic matter. Everything appears to line up. But a crucial question lurks beneath the surface, one that determines whether gravastars belong to the realm of real astrophysical phenomena or remain confined to the realm of theoretical speculation. Are gravastars actually stable? Can such delicate cosmic structures withstand the chaotic violence of their birth and the harsh tests of the universe? To answer that, physicists have explored the mathematical foundations of gravastars under every kind of stress: perturbations, deformations, quantum fluctuations, and gravitational instabilities. Because even if a gravastar is theoretically valid, it means little unless it can persist. The universe is a brutal environment. Any viable object must endure not just a moment of equilibrium but the test of time, accretion, radiation, and tidal forces. The gravastar structure, on a basic level, is a tripartite model: a central vacuum, or gravitational condensate, an ultra-thin shell of exotic matter, and the exterior spacetime resembling a Schwarzschild geometry. The central vacuum has negative pressure, a kind of dark energy that pushes outward. The shell, by contrast, is extremely compact and dense, and it pushes inward due to its mass and tension. It's this delicate balance, outward vacuum pressure countering inward gravitational tension, that creates the so-called equilibrium. But equilibrium doesn't automatically imply stability. Mathematically, stability means that if the system is slightly perturbed, nudged, compressed, or expanded, it doesn't spiral out of control. Instead, it returns to a new or restored equilibrium. For gravastars, this leads us into the realm of linear and nonlinear perturbation theory, where physicists test how such objects react when exposed to slight disturbances, such as a passing gravitational wave, the accretion of infalling matter, or minute quantum instabilities. Early models of gravastars by Mazur and Motola showed that under idealized conditions, spherical symmetry, perfect vacuum core, and precise shell properties, the system could be stable. But these models were static, meaning they didn't evolve in time. So researchers asked, what happens if the shell is pushed slightly inward or outward? Does it oscillate and return, or does it collapse? Subsequent studies introduced dynamical models, allowing the shell to move under perturbation. Some found that the shell could oscillate around an equilibrium radius, returning to stability under certain conditions, a sign of a potentially stable gravastar. But these studies also revealed that stability depends heavily on the properties of the shell, its equation of state, thickness, energy density, and how it reacts to compression. If the shell's internal pressure isn't fine-tuned just right, the gravastar might either collapse into a black hole or explode outward like a failed vacuum bubble. This is where one of the gravastar's most criticized aspects comes in: the exotic matter that makes up the shell. It must violate classical energy conditions, specifically the null energy condition, which is a fancy way of saying that it must have properties no ordinary matter can possess. It must exert negative energy or pressure in certain directions. While quantum theory allows for such states in small regions, as seen in the Casimir effect, whether such exotic matter can exist macroscopically and remain dynamically stable is still unknown. Another concern involves rotation. Real astrophysical objects don't sit still, they spin. Often, they spin rapidly. Introducing rotation into gravastar models adds layers of complexity. The centrifugal forces acting on the shell, the frame-dragging effects on the surrounding spacetime, and the anisotropic pressures inside all affect the delicate balance of the structure. Some studies suggest rotating gravastars may remain stable up to certain spin thresholds, but beyond that, instabilities can arise, similar to the way a spinning top wobbles and eventually falls when pushed too far. Furthermore, accretion, the process of gathering surrounding matter, is a reality for any compact astrophysical object. If a gravastar accumulates enough mass through accretion, especially unevenly, it may disturb the balance between the shell and the vacuum core. If the inward pressure becomes too great, or the shell's density surpasses a critical threshold, it could lead to gravitational collapse, forming a black hole after all. Conversely, a strong enough outward disturbance might cause the shell to burst, releasing the vacuum energy inside in a catastrophic event, possibly resembling a gamma-ray burst or some other high-energy transient phenomenon. Quantum stability is another concern. The vacuum interior of a gravastar is often described as a false vacuum, a metastable state that might not represent the lowest possible energy configuration of the universe. If that's true, then a gravastar could be vulnerable to quantum tunneling. A small fluctuation or interaction could cause the vacuum core to decay into a lower energy state, potentially causing the entire structure to collapse or explode. Though such events would be incredibly rare, they introduce a fundamental fragility to the concept. Despite these concerns, it's important to note that some gravastar models do pass stability tests, especially under controlled assumptions. In particular, the so-called thin shell gravastar models, where the shell is treated as a hypersurface with specific energy momentum conditions, have shown promising stability across a range of parameters. When the pressure profile, radius, and energy density are carefully selected, the resulting object can survive perturbations, accretion, and even modest rotation. Still, this requires an almost surgical level of precision in the balance of forces, something critics argue may be too fine-tuned to occur naturally. A star collapsing into a gravastar would need to undergo a highly specific series of events and produce just the right kind of shell with the right equation of state. It might not be impossible, but it could be extraordinarily rare. And yet nature has surprised us before. Neutron stars, pulsars, and magnet-stars, each was once thought to be too extreme to exist until we observed them. It's possible that gravastars, too, occupy that strange intersection between improbable and inevitable. Their formation may be rare, but given the sheer scale of the cosmos, even rare events happen countless times. In conclusion, the debate over gravastar stability remains open. The mathematics shows that under the right conditions, gravastars can be stable. But whether those conditions exist in the messy, dynamic reality of the universe is another matter. It's a question that touches on the most delicate interplay between gravity and quantum mechanics. The final answer may not only determine the fate of gravastars but also the limits of black holes, the nature of cosmic collapse, and whether spacetime itself can hold secrets stranger than singularities. The idea of a gravastar, a structure so extreme it balances the crushing force of gravity with the outward push of vacuum energy, sounds like pure science fiction. And perhaps it is, for now. But science fiction has a habit of becoming science fact, and the question inevitably arises, could we ever create something like a gravastar in a laboratory setting? Could the same principles that govern the birth and balance of these cosmic anomalies be simulated, replicated, or at least approximated with the tools of Earth-based physics? At first glance, the answer seems a resounding no. Gravastars are theoretical objects formed from the collapse of massive stars, stellar remnants with several solar masses, subject to gravitational forces far beyond anything we can recreate on Earth. The core of a gravastar is thought to consist of dark energy, or a gravitational vacuum condensate, surrounded by a microscopically thin shell of exotic matter, all contained within a compact radius close to the Schwarzschild limit. These are not the kinds of materials you can just order in a laboratory catalog. But still, physicists have explored whether some analog systems or scaled-down approximations could help us understand their structure, or even simulate their behavior. To begin, let's consider what makes a gravastar fundamentally unique. It's not just the immense gravity or the density, but the interaction between vacuum energy, exotic matter, and space-time curvature. These aren't isolated phenomena. They touch upon concepts that quantum physicists and cosmologists are actively probing. So while we cannot collapse a star in a lab, we might be able to simulate the physics that emerges from such a collapse. One approach comes from the field of analog gravity. This area of research explores physical systems that mimic certain behaviors of gravitational systems using completely different materials. For example, flowing fluids, optical media, and even Bose-Einstein condensates can be manipulated to simulate horizons, space-time curvature, and Hawking radiation. These systems do not involve real gravity, but they reproduce the mathematical structures of general relativity in other media. In fact, in 1981, physicist William Unruh first proposed that sound waves in a fluid flowing faster than the speed of sound could mimic the behavior of light near a black hole event horizon. Since then, experimentalists have created acoustic black holes, or dumb holes, where sound cannot escape a region of flow, in much the same way light cannot escape a black hole. This demonstrates that horizon-like behavior can indeed be created in controlled environments, at least in analog form. Could this extend to gravastars? Some researchers think so. In 2004, theoretical physicists suggested that Bose-Einstein condensates, BECs, a state of matter where atoms behave like a single quantum entity, might be used to simulate the structure of a gravistar. The idea is that a BC could be engineered to produce pressure gradients and phase transitions similar to those found in the gravistar model. The center of the BC could act as an analog for the vacuum condensate core, while the outer edges could be manipulated to simulate a thin shell of high-density matter. Though the forces and scales involved are drastically different, the underlying mathematics, the field equations and boundary conditions, can be matched under certain approximations. Some laboratory experiments have already achieved crude analogs of event horizon-like structures in superfluid helium, optical fibers, and ultra-cold atomic gases. The recent creation of synthetic black holes in photonic systems and simulated Hawking radiation in BECs suggests that gravistar-like behavior could be probed in similar setups. These analogs can't capture the full breadth of the gravitational equations involved, but they provide insight into how such structures behave under perturbation, how they trap waves, and how they might reveal themselves through radiation. The next question is whether we can recreate or test vacuum energy in the lab, the ingredient that supposedly forms the interior of the gravistar. In our universe, vacuum energy is related to dark energy, the mysterious force accelerating the expansion of the cosmos. We cannot isolate or bottle dark energy, but we can explore phenomena that involve vacuum fluctuations and negative pressure, and we already have. One famous example is the Casimir effect, a quantum mechanical phenomenon in which two uncharged metal plates placed extremely close together experience an attractive force due to vacuum fluctuations. This is experimental proof that the quantum vacuum is not empty, but filled with fluctuating fields that exert real, measurable pressure. In a sense, this is the microscopic cousin of the kind of negative pressure theorized in gravistar cores. Another experiment in this direction involves metamaterials, artificial materials designed to have properties not found in nature, such as negative refractive index. By manipulating how waves, light, sound, or other fields propagate through them, researchers can create environments where energy behaves counterintuitively. In theory, a carefully constructed metamaterial could mimic the shell of a gravistar, or at least simulate how it interacts with surrounding fields. There are also efforts underway to create quantum simulations of space-time geometry using networks of entangled quantum bits. In the future, these might allow researchers to reconstruct simple models of curved space, horizons, and vacuum structures, not in physical materials, but in quantum circuits. With quantum computing advancing rapidly, it's not unreasonable to imagine that digital gravistar simulations could one day probe the stability and behavior of these exotic stars from within a lab. Yet all of this must be placed in proper perspective. These are analogs and simulations, not actual gravastars. We cannot, with current technology, generate the gravitational field of a neutron star, let alone the delicate vacuum structure of a gravistar. We cannot compress matter to Planck densities, manipulate the cosmological constant, or maintain stable shells of exotic matter in three-dimensional space. The energy scales, curvatures, and pressures required are many orders of magnitude beyond our reach. But that doesn't mean we're helpless. By building laboratory analogs, physicists can test how certain features behave, how light is trapped, how shells respond to stress, how wave echoes form, or how vacuum states transition under changing parameters. These experiments help validate or falsify the assumptions that go into gravastar models. If gravastar analogs exhibit instability under specific conditions, that might hint at flaws in the real astrophysical version. If, on the other hand, they maintain stable horizons or mimic gravitational wave echoes, they might bolster the argument that gravastars could indeed exist. In essence, the lab becomes a miniature cosmos, not in terms of scale, but in terms of behavior. It's here, in these constrained, carefully controlled environments, that we might learn whether nature permits gravastars at all, or whether they're just mathematical phantoms. So while the dream of building an actual gravastar in a laboratory is, for now, beyond reach, the spirit of the experiment is very much alive. And as our control over quantum states, metamaterials, and simulation technology grows, we may inch ever closer to touching the untouchable, probing the nature of exotic stars, and even of space-time itself, from the confines of Earth. The black hole information paradox is one of the greatest unresolved tensions in modern theoretical physics, a clash between the smooth, continuous fabric of general relativity and the unforgiving logic of quantum mechanics. It suggests that if black holes truly evaporate through Hawking radiation, and that radiation is purely thermal and contains no information, then the universe is capable of destroying information. But that can't be, according to quantum theory. Quantum information is not supposed to vanish. It may be scrambled, dispersed, entangled, or delayed, but it must always be preserved. And here, in this grand conflict, is where gravastars step onto the stage with a bold proposal. Perhaps the paradox is not a flaw in physics, but a misunderstanding of the object itself. To appreciate how gravastars might solve the information paradox, we must first review the key elements of the paradox itself. In the standard black hole model, any matter or information that crosses the event horizon is lost to the external universe. From the outside, an observer sees only the mass, charge, and spin of the black hole, not what fell into it. Over time, the black hole emits Hawking radiation, a quantum effect near the horizon where virtual particles become real. But this radiation appears to carry no information about the interior. Eventually, the black hole evaporates entirely. And with it, if the radiation is truly featureless, all information about what it once contained vanishes. This violates quantum unitarity, the principle that information must be conserved in any physical process. This is not just an academic issue. It's a foundational one. If black holes destroy information, then physics loses its predictive power. The laws of the universe would become probabilistic in a way far deeper than quantum mechanics allows. And so, physicists have struggled for decades to resolve the paradox, offering ideas ranging from holographic principles, firewall hypotheses, to entanglement wedges and quantum error correction codes embedded in space-time geometry. Gravastars offer an elegant and comparatively simple solution. What if black holes never formed an event horizon in the first place? In the gravastar model, the collapsing star doesn't create a singularity surrounded by an event horizon. Instead, the collapse is halted just before that critical point by a transition to a vacuum-like state, perhaps a gravitational Bose-Einstein condensate. This inner vacuum has a repulsive pressure that counters gravity, and the matter of the star is compressed into a thin shell. The result is an object that mimics the external gravitational field of a black hole, so much so that, observationally, it might be indistinguishable. But crucially, there is no true event horizon. Why does this matter? Because without an event horizon, information isn't irretrievably lost. In a gravastar, matter may fall into the object, but it never crosses a point of no return. Instead, it strikes the shell, or in some models, is absorbed into the vacuum structure in a way that preserves its quantum state, even if in highly transformed or encoded form. This implies that information could, in principle, be retained within the gravastar, or even re-emitted slowly over time. Moreover, because there is no singularity, there is no infinitely compressed point where known laws of physics break down. That means quantum field theory may remain valid throughout the entire gravastar structure. The vacuum core may interact with quantum fields in non-destructive ways, Instead of information being crushed out of existence, it is encoded in the shell, stored in quantum correlations, or radiated away in subtle forms, possibly even through deviations in the Hawking-like radiation emitted by the shell. Some gravastar models go further, proposing that the shell could act as a quantum reflector. When virtual particle pairs form near the boundary, rather than one particle falling in and the other escaping, as in the Hawking process, the inner particle might bounce off the shell, conserving entanglement. In this way, the emitted radiation wouldn't be thermal and featureless. It would carry imprints of the matter and energy that previously interacted with the gravastar, satisfying unitarity and preserving information. Over very long timescales, the gravastar might emit its contents back into the universe, subtly, gradually, and without paradox. This idea resonates with the concept of the fuzzball in string theory, a model where black holes are replaced by a tangle of quantum strings, each carrying information and eliminating any central singularity or true horizon. Gravastars may be viewed as a more classical or geometrical version of this idea, where instead of a tangled string configuration, a stable shell and vacuum core hold and distribute information. There's also another angle. In standard black holes, the paradox arises because once something crosses the event horizon, there's no way to retrieve it. But gravastars allow for a non-destructive internal structure. A signal may not escape easily, but it isn't fundamentally prohibited from doing so. The shell may reflect, echo, or emit information in unusual ways. In fact, some theorists have proposed that gravitational wave echoes, if ever detected reliably, could be the voice of a gravastar, information trapped and released in reverberations from its inner boundary. Another critical point, even if the emission from a gravastar looks thermal from a distance, like Hawking radiation, the lack of a true horizon allows for small corrections to accumulate. Over long durations, those corrections could restore the information content, satisfying what is known as the page curve, a prediction from quantum theory that describes how information returns during black hole evaporation. Black holes struggle to explain the page curve without invoking radical new physics. Gravastars may explain it naturally, simply by not being true black holes at all. Still, it's not all straightforward. While gravastars avoid many of the logical traps of black holes, they come with their own uncertainties. How exactly does information interact with the shell? Is it stored in a holographic fashion on the shell's surface? Is the vacuum condensate stable enough to preserve subtle quantum states? Does the lack of an event horizon really ensure complete information recovery, or do we simply trade one mystery for another? Yet despite these challenges, gravastars offer a rare thing in theoretical physics, a model that not only aligns with known physics, but one that sidesteps paradoxes rather than explaining them away with speculative principles. By proposing that event horizons are illusions, and that singularities are avoided, gravastars let us preserve unitarity without needing firewalls, ER=EPR wormholes, or radical departures from locality. In this way, gravastars could resolve the black hole information paradox, not by patching it, but by rendering it obsolete. If black holes aren't truly the endpoint of gravitational collapse, if what we see as a black hole is actually a gravastar in disguise, then the problem of lost information dissolves. Information, like matter and energy, may simply be waiting, stored in the shell, whispered through echoes, or radiated slowly from the vacuum core. And in that possibility lies a quiet revolution. Perhaps the universe is not as final as we feared. Perhaps the cosmos remembers more than we ever dared imagine. If gravastars already bend the laws of physics, wormholes tear through them completely. At least, that's how they've long been imagined. Both are exotic theoretical constructs born at the edge of Einstein's equations, where space and time lose their familiar shapes. One forms in the aftermath of a dying star. The other potentially opens a bridge between distant regions of the universe, or perhaps even between universes themselves. And yet they share something profound. Both arise from a rejection of singularities, both require exotic matter, and both stretch the fabric of spacetime to its limits. This overlapping strangeness has led physicists to ask a tantalizing question: could gravastars and wormholes be related? Could they even be different expressions of the same deeper geometry? To explore this idea, we have to recall what a wormhole truly is in general relativity. Formerly called an Einstein-Rosen bridge, a wormhole is a hypothetical tunnel through spacetime, connecting two separate locations via a shortcut. In the standard black hole model, a Schwarzschild black hole does contain a mathematical wormhole, but it's unstable, non-traversable, and pinches off faster than light can cross it. Useful wormholes, ones you could travel through, require something more: exotic matter that can resist gravitational collapse and keep the tunnel open. And here's where the connection to gravastars begins. A gravastar, by definition, is surrounded by a shell of exotic matter that violates classical energy conditions and can produce negative pressure. This is exactly the kind of material wormholes require to remain traversable. In fact, some versions of the gravastar model, particularly those with extremely thin shells or variable internal vacua, can be mathematically transformed into wormhole-like solutions under certain conditions. The shell doesn't just resist collapse. In specific models, it can reflect or refract geodesics, bending the paths of light and matter much like a wormhole throat would. In 2006, researchers began to explore these similarities more explicitly. They proposed that if the vacuum energy inside a gravastar had a particular configuration, like a variable equation of state or anisotropic pressures, then the spacetime it generated could extend not into a singularity or boundary, but into another region of spacetime entirely. In this sense, the core of a gravastar could be the mouth of a wormhole, its shell acting as a gateway. This wormhole would be hidden from the outside world by the apparent event horizon-like behavior of the gravastar. From a distance, it might appear to be just another black hole mimic. But up close, or from within, it could be something far stranger, a passage to elsewhere. Some versions of this idea go further. They imagine that two gravastars, each with their own vacuum cores and exotic shells, could be entangled across a shared geometry, effectively forming the two mouths of a traversable wormhole. This is where the theory starts to echo ER equals EPR, a bold conjecture from quantum gravity suggesting that Einstein-Rosen bridges, wormholes, and quantum entanglement, Einstein-Podolsky-Rosen pairs, are not separate ideas, but two sides of the same coin. In this view, space-time connectivity itself emerges from entanglement, and exotic objects like gravastars may act as natural structures where this duality plays out. Even more exotic is the proposal that the interior of a gravastar is not a dead-end vacuum, but a dynamically connected region of space that could route signals, or even particles, through the shell and out into another part of the universe. Some speculative papers have modeled gravastars with topological connections that mirror those of wormholes, toroidal geometries, ring-like structures, or multiply connected manifolds. These geometries, while mathematically consistent with general relativity and exotic matter assumptions, remain deeply speculative, but they suggest that gravastars may not simply trap matter. They might redirect it. Another angle of connection comes from stability analysis. Traversable wormholes are notoriously unstable, especially to quantum fluctuations, tidal forces, or even the presence of a single particle. However, gravastars, particularly those with rigid shells and inward pressure from vacuum energy, may provide a stabilizing structure. In this view, a gravastar could serve as a wormhole stabilizer, its shell acting as a kind of buffer between two vacuum regions. This has led some physicists to propose that gravastars might be a viable architecture for constructing stable wormholes, if one ever figured out how to build such things. But there's an even more radical possibility, that wormholes and gravastars are not just connected concepts, but that they are fundamentally the same object seen from different perspectives. A gravastar may look like a black hole mimic from one vantage point, but to something inside, or connected via a quantum bridge, it may serve as a conduit. In this interpretation, gravastars don't just avoid singularities, they replace them with bridges. They don't just store information, they route it, perhaps non-locally, through the quantum geometry of spacetime. This also connects to the information paradox. If information falling into a black hole is truly lost, the paradox remains. But if that information instead passes through a gravastar and emerges elsewhere, say, through a wormhole mouth, the universe preserves unitarity, no paradox needed. In this way, gravastars may solve not just the problem of singularities or event horizons, but the puzzle of space-time connectivity itself. Still, the wormhole gravastar duality remains speculative. There is no direct observational evidence for either structure, and many of the mathematical connections rely on idealized conditions, perfect symmetry, specific energy distributions, or exotic matter with properties we cannot yet produce or confirm. And wormholes, in particular, raise deep questions about causality, time travel, and the structure of the universe, questions gravastars, as currently modeled, do not address. Yet the link is hard to ignore. Both objects challenge our assumptions about gravity. Both rely on exotic states of matter. Both avoid the central singularities that plague black holes. And both stretch the limits of space-time in ways that force us to ask whether the universe is more connected, more strange, than we ever dared to imagine. If gravastars and wormholes are connected, even subtly, then these theoretical monsters may hold the key not just to astrophysics or quantum gravity, but to how the cosmos knits itself together, across distances, across time, and perhaps across reality itself. Light, our most faithful messenger in the cosmos, reveals the nature of space itself by the paths it takes. Around black holes, light follows the dramatic curves of warped spacetime, spiraling in chaotic orbits, skimming horizons, and in some cases vanishing forever past the point of no return. Gravastars, while outwardly similar to black holes, possess internal structures so radically different that the behavior of light near them tells a subtly, but profoundly, different story. Understanding how light bends, echoes, or orbits around a gravastar might be the key to distinguishing these cosmic imposters from the real thing, and perhaps, glimpsing one of the strangest structures the universe has ever conceived. From afar, a gravastar's gravitational pull can mimic that of a black hole almost perfectly. The shell and vacuum interior are compressed to such an extreme degree that the external geometry is described by the Schwarzschild metric, just like a non-rotating black hole. This means that light traveling at a distance sees no difference. It curves, redshifts, and orbits as expected. But move closer, and the story begins to change. First, consider the concept of the photon sphere, a spherical region of spacetime where photons, particles of light, can orbit a massive object in a circular path. For a Schwarzschild black hole, this occurs at 1.5 times the Schwarzschild radius. Photons that hit this region perfectly can circle indefinitely in unstable orbits. In practice, they tend to spiral inward or outward with the slightest perturbation. Gravastars also exhibit a photon sphere, because their outer gravitational field closely mimics that of a black hole. However, unlike black holes, gravastars lack an event horizon. Instead of spiraling into a void, light that approaches the gravastar's shell is either reflected, refracted, or even echoed, depending on the shell's properties and the energy of the photon. The internal vacuum repels matter and energy due to its negative pressure, and this repulsion can subtly influence how light behaves near the shell. This sets up a scenario where light doesn't fall in and disappear, but instead bounces, gets delayed, or even echoes back in complex ways. If the shell is partially reflective, as some models suggest, then a fraction of incoming light could be trapped in quasi-bound states, orbiting just outside the shell for extended periods before escaping. These photon echoes would appear as repeating pulses of light or gravitational radiation, arriving after the main emission. In the case of gravastars merging or accreting material, this could produce detectable signals unlike anything a classical black hole would emit. Some theoretical studies have modeled this behavior and found that gravastars can produce distinct light curves during events like mergers or flare-ups. For example, when a gravastar interacts with infalling matter, the light doesn't simply disappear behind a horizon. Instead, it gets reprocessed by the shell, sometimes scattering multiple times before escaping. The result is a delayed and possibly modulated light emission, a kind of luminous afterglow that could reveal the object's exotic internal geometry. The lensing behavior near a gravastar is also subtly altered. In gravitational lensing, massive objects bend the paths of light from background sources, creating arcs, rings, or multiple images. A gravastar's lensing profile closely resembles that of a black hole, especially at large distances. But near the shell, differences emerge. Light paths that would have terminated at a black hole's horizon instead get reflected or deflected back into space, slightly changing the shape and intensity of the lensed image. For instance, one notable effect is the predicted absence of a shadow core. The black hole, shadow, seen in images like those from the Event Horizon Telescope represents a region from which no light escapes. A gravastar, by contrast, may produce a shadow that's less dark or sharply defined, because light isn't swallowed by an event horizon but instead interacts with the shell. Some of it may scatter or be emitted later, filling in the central darkness with a faint glow or echoes. Future imaging with higher precision could, in theory, detect such distinctions. The shell itself plays a critical role in shaping light behavior. Depending on its composition and properties, such as whether it behaves like a superfluid, a condensate, or an anisotropic layer, it could interact with photons in unexpected ways. Some models suggest that light incident upon the shell at shallow angles could experience total internal reflection, bouncing along the shell's surface in a manner akin to fiber optics. Others propose that photons could enter the shell, slow down due to an effective refractive index, and exit in altered trajectories, creating subtle distortions in the outgoing light patterns. Even more intriguing is the possibility of whispering gallery modes, phenomena where waves, including light, become trapped by circular reflection in curved geometries. If a gravastar's shell supports such modes, it might create resonant rings of light, storing and slowly releasing energy over time. These structures could produce very specific spectral or polarization signatures, perhaps detectable with future observatories sensitive to faint echoes or high-resolution spectra. Then there are the implications for light travel time. Near a black hole, time dilation causes signals from near the horizon to appear stretched, slowing down and redshifting until they vanish. Gravastars produce similar but ultimately finite delays. Signals from near the shell may seem to slow dramatically due to gravitational time dilation, but they don't halt. Over time, they can re-emerge. This creates the possibility for reverberating light curves, where the same event produces multiple pulses of light spread over long durations. Finally, quantum light-matter interactions near gravastars may exhibit unique behavior. The boundary between a vacuum condensate and a shell of exotic matter could act like a non-classical quantum surface, possibly entangling, reflecting, or altering photons in ways that violate simple expectations. If gravastars interact with radiation fields differently from black holes, that could imprint subtle quantum signatures in the spectrum of observed light, small but measurable deviations from thermal profiles. In summary, the behavior of light near a gravastar may be the most direct and revealing signature of its true nature. From echoes and lensing anomalies to time delays and resonance effects, light doesn't simply vanish. It dances, it traces the shell, it remembers. And if we build instruments sensitive enough to detect these patterns, we may one day distinguish gravastars from black holes, not by their mass, not by their shadow, but by the shimmering, whispering traces they leave in the light that dares to come near. When LIGO first detected gravitational waves in 2015, the world was shaken, not by the waves themselves, which stretched and compressed spacetime by mere fractions of a proton's width, but by what those waves revealed. Two black holes, spiraling together in a cataclysmic merger over 1 billion light-years away, had collided in a final dance of unimaginable violence. The resulting ripple in spacetime arrived at Earth after traveling across the cosmos, confirming a century-old prediction from Einstein's theory of general relativity. But as we listen closer to these cosmic symphonies, some physicists began to wonder, what if we weren't hearing black holes? What if the signals came from something far stranger, objects that mimic black holes in many ways, but leave behind a slightly different signature in the gravitational song? What if some of LIGO's detections were not the voices of black holes, but the whispers of gravastars? To answer this, we must look at what gravitational waves really are: oscillations in spacetime caused by the acceleration of massive objects, particularly in violent, asymmetric events like mergers or collapses. The shape, frequency, and decay of these waves tell us a great deal about the nature of the objects involved, their masses, their spins, and most intriguingly, the structure of their event horizons or lack thereof. Black hole mergers, in particular, have a very distinct waveform structure. It begins with the inspiral phase, where two black holes orbit one another, radiating energy and drawing closer. Then comes the merger, where they collide and form a single, distorted black hole. Finally, we enter the ring-down phase, where the remnant black hole settles into a stable state, emitting gravitational waves that decay in frequency and amplitude over time, a cosmic death rattle of sorts. If gravastars exist, and if they can merge like black holes, we would expect the inspiral phase to look nearly identical. That's because, from a distance, gravastars exert gravitational fields nearly indistinguishable from black holes of the same mass. The orbital dynamics would remain the same, and the gravitational waves emitted would follow the predictions of general relativity very closely, at least until the moment of collision. But here's where things get interesting. In a black hole merger, the final object has an event horizon. It traps all matter and radiation, and no signal ever escapes from within. The ring-down waveform, in this case, is dominated by quasi-normal modes, specific vibrational frequencies determined entirely by the mass and spin of the black hole. These modes decay exponentially as the system stabilizes. The waveform is clean, final, and devoid of echoes. Gravastars, on the other hand, do not possess an event horizon. Instead, they have a physical surface, or at least a boundary layer composed of exotic matter. When two gravastars merge, the collision may produce initial waves nearly identical to a black hole merger, but the absence of a true horizon could lead to a very different post-merger behavior. One of the key predictions of gravastar models is the existence of gravitational wave echoes. These are faint, delayed repetitions of the original ring-down signal, caused by gravitational waves bouncing back and forth between the inner vacuum and the outer shell before escaping. In other words, instead of being swallowed by a horizon, the gravitational waves reverberate within the gravastar's structure, eventually leaking out in a series of fading pulses, like sound echoes in a hollow room. These echoes would not appear instantly. They would arrive milliseconds to seconds after the main ring down, depending on the size and compactness of the gravastar. The echoes would also have a slightly different frequency profile and decay pattern compared to the initial wave. Detecting such a signal would require incredibly precise instruments and careful filtering to distinguish from background noise. Interestingly, some early reanalyses of LIGO data hinted at possible evidence for echoes. In 2016, just months after LIGO's first detection, a group of physicists reported faint secondary signals following the ring-down phase of one of the events, signals that could be interpreted as echoes from a horizonless object. The evidence wasn't conclusive, and the scientific community remains divided. Some subsequent studies supported the finding, while others argued the data was inconclusive or likely a statistical artifact. Still, the possibility remains open. If even a single merger event shows consistent, repeatable echoes, it could shake the foundations of astrophysics. It would suggest that not all compact objects with extreme gravity are black holes, and that some may be gravastars, or other exotic horizonless objects like boson stars, wormholes, or fuzzballs. Beyond echoes, gravastar mergers might also produce slightly different ring-down frequencies compared to black holes. The exact shape of the waveform depends on the object's internal structure and boundary conditions. A gravastar's shell may respond differently to the stress of merging, causing deviations in the vibrational modes. These differences may be subtle, requiring advanced waveform templates and machine learning algorithms to detect. But with the increasing sensitivity of detectors like LIGO, Virgo, CAGRA, and the upcoming LISA, Laser Interferometer Space Antenna, the window to explore these deviations is rapidly widening. Another area of investigation involves the merger aftermath. Black holes, after merging, rapidly settle into a new stable horizon. But gravastars might undergo a more chaotic transition. The merging shells could cause turbulence in the vacuum core, create temporary instabilities, or even trigger oscillatory behaviors that emit unique gravitational wave patterns for longer durations. These patterns would not just echo but potentially modulate the waveform, creating distinctive fingerprints that could distinguish gravastar mergers from classical black holes. Moreover, some theories suggest that gravastars might emit additional types of radiation, not just gravitational, but electromagnetic or even neutrino bursts, if their structure is disrupted during a merger. These signals could accompany the gravitational wave event, providing multi-messenger evidence for exotic compact objects. All of this remains speculative but tantalizingly within reach. Gravitational wave astronomy is still in its infancy, yet it's already transforming our understanding of the universe. The idea that we might detect the signatures of gravastars, not through direct observation, but through the whispers they leave in spacetime itself, is a testament to the precision and depth of modern physics. As detection technology improves, as more mergers are observed, and as waveform modeling grows more sophisticated, we may soon be able to tell whether we're hearing black holes or something far stranger. And if gravastar signatures are ever confirmed, it would mean we've already been witnessing them. We just didn't know how to listen. For decades, astronomers have watched with awe as stars disappeared, galaxies twirled with invisible gravitational centers, and gravitational waves rippled from colossal mergers. The verdict has seemed unanimous. These must be black holes. They bend light, influence stars, trap time, and sometimes vanish behind a veil of nothingness. But what if we've been deceived by nature's greatest illusionist? What if some, perhaps many, of these black holes are actually something else entirely? Could they be gravastars, cloaked in the same gravity, yet fundamentally different in structure? This is not just idle speculation, it's a question that pierces to the heart of observational astrophysics. Because gravastars, by design, are masters of disguise. Their external gravitational field is indistinguishable from that of a black hole. They form from the collapse of massive stars, just as black holes do. They can match a black hole's mass, spin, and radius almost perfectly. From far away, no telescope, no lensing arc, no orbiting star can betray the secret. They look exactly like black holes. And that's the central mystery. When we say we've seen black holes, we mean we've seen their gravitational influence on stars, on matter, on light. We've watched stars like S2 whip around the galactic center near Sagittarius A, revealing a compact object millions of times the mass of our Sun. We've observed the dramatic jets from accretion disks, where matter swirls into oblivion at relativistic speeds. We've captured the iconic shadow of M87 with the Event Horizon Telescope. And we've felt the tremors of spacetime as merging black holes crashed into each other a billion light-years away. But in none of these cases have we observed the singularity, the event horizon, or the actual interior of a black hole. What we've seen are the effects, not the entity itself. This ambiguity opens the door wide for alternatives like gravastars. Since gravastars mimic the external geometry of a Schwarzschild black hole, they pass all current observational tests, up to the horizon. If the object's radius is within a few Planck lengths of the Schwarzschild radius, no light escapes. It's dark, opaque, silent. But that doesn't necessarily mean it's a black hole. Some researchers argue that the very darkness we attribute to the event horizon might, in fact, come from the gravitational vacuum shell of a gravastar, which, while incredibly compact, does not trap information permanently. Unlike an event horizon, which marks the boundary of no return, a gravastar's shell might reflect or delay light in ways that are observationally similar, but subtly distinct. It might even re-emit energy or radiation in forms we've mistaken for Hawking radiation or thermal noise. Moreover, recent developments in gravitational wave astronomy raise further questions. The ring-down phase of LIGO-detected black hole mergers, as previously discussed, sometimes shows hints, subtle, controversial hints, of echoes. These echoes are not predicted by classical black hole physics but are expected in gravastar models, due to reflections between the vacuum core and the shell. Could it be that some of the compact object mergers we've detected aren't black holes at all, but horizonless gravastars whose interiors remain intact? Let's take a moment to consider specific astrophysical candidates. The supermassive object at the center of the Milky Way, Sagittarius A, is an ideal case. It's massive, it's dark, and stars orbit it at high speeds, obeying general relativity's predictions. But does that prove it's a black hole? Not conclusively. It proves only that a compact object of sufficient mass lies at that location. If that object is a gravastar with a radius just marginally above the Schwarzschild limit, it would have the same gravitational fingerprint. In fact, it would be impossible, with current instruments, to tell the difference. Likewise, many stellar mass black holes discovered in X-ray binaries, systems where a visible star orbits an invisible partner, could theoretically be gravastars. Their observed properties match expectations: intense X-ray emissions from hot accretion disks, gravitational lensing, rapid orbital motion. But the internal structure of the compact object remains hidden. If the surface of the gravastar is non-reflective or absorbs infalling matter with high efficiency, we would see no difference in the emission patterns. In some cases, accretion signatures could even help support the gravastar hypothesis. If anomalous delays or emission spectra are observed that can't be explained by black hole models. Then there's the intriguing idea of mass gaps, ranges where black holes seem to be rare or missing. For instance, the so-called parent stability mass gap between 50 and 120 solar masses is a region where traditional stellar evolution models suggest black holes shouldn't form. Yet gravitational wave detectors have observed merger remnants with masses in this range. Could some of these impossible black holes be gravastars instead? Formed by different mechanisms, stabilized by exotic matter, existing in defiance of classical collapse rules. One of the strongest arguments in favor of the gravastar hypothesis is theoretical cleanliness. Black holes, as elegant as they are, come with baggage, singularities that tear space-time apart, event horizons that trap information forever, paradoxes that challenge quantum mechanics. Gravastars avoid all of this. No singularity. No true horizon. No information loss. If gravastars exist and can form naturally in the universe, then Occam's razor might favor them over black holes, at least in some cases. However, we must also confront the elephant in the room. There is still no direct observational evidence for gravastars. No gravitational wave echo has yet been unambiguously detected. No light curve anomaly has been definitively attributed to a gravastar surface. No deviation from black hole predictions has forced us to adopt the gravastar model. The hypothesis remains elegant but unconfirmed. That said, the era of precise astrophysical measurement is only just beginning. The next generation of observatories, the Laser Interferometer Space Antenna, LISA, the Extremely Large Telescope, ELT, the James Webb Space Telescope, JWST, and upgrades to the Event Horizon Telescope, will open new windows into the behavior of compact objects. These tools may finally probe the region near the event horizon with enough detail to spot the differences: tiny deviations in light curves, unexpected gravitational wave echoes, or unusual frequency modes in the ring-down phase. In the meantime, we're left with a fascinating and humbling possibility that some of the black holes we've celebrated as conquests of Einstein's theory are not black holes at all. They are imposters, cosmic doppelgangers made not of collapsed infinities, but of vacuum energy, exotic matter, and structures far stranger than fiction. They lurk in the same shadows, emit the same gravitational pull, and dance in the same space-time, yet at their heart, they tell a different story. Perhaps the universe has been whispering it to us all along. We just haven't listened closely enough. Time is not a constant drumbeat across the universe. It is elastic, stretched and warped by gravity. This strange consequence of Einstein's general relativity becomes extreme near compact objects like black holes, where time slows to a crawl as one approaches the event horizon. For an outside observer, anything falling in seems to freeze in place, eternally suspended on the edge of darkness. This phenomenon, known as gravitational time dilation, isn't just science fiction. It's been confirmed by satellite clocks and GPS systems, and it shapes our understanding of reality near dense masses. But what happens near a gravastar, an object that mimics a black hole in many ways but lacks a singularity and an event horizon? Could time near a gravastar slow just as dramatically? Or does its exotic internal structure lead to even stranger effects? To understand time near a gravastar, we first need to recall how time dilation works around massive objects. In simple terms, the stronger the gravitational potential, the deeper the gravity well you are in, the slower time flows relative to a more distant observer. For example, on Earth, clocks tick ever so slightly slower at sea level than they do on mountaintops. Near a neutron star, the effect is far more pronounced. Near a black hole, time dilation becomes extreme, approaching infinity at the event horizon. Gravastars push this concept to the edge. Although they do not have event horizons, they are still incredibly compact. Their radius may be just infinitesimally larger than the Schwarzschild radius of a black hole with the same mass. That means the gravitational potential at their surface is nearly as deep as that of a black hole, and therefore, the time dilation is nearly as severe. To an observer far from the gravastar, a clock resting just above its surface would appear to tick incredibly slowly. In fact, depending on how close the surface is to the Schwarzschild radius, the difference could be enormous. If the surface lies just a few Planck lengths above that limit, the redshift, and therefore the time dilation, becomes so extreme that it is effectively indistinguishable from that of a black hole. The difference would be subtle, hidden in fractional deviations in redshift or timing, but fundamentally, time would still move forward at the surface. Just very slowly. This has profound consequences. Let's imagine an astronaut hovering just above a gravastar's surface, safely sustained in place by propulsion. From their perspective, time feels normal. Their heartbeat, their thoughts, their instruments, all run at regular speed. But if they look outward, into space, they would see the universe racing by. Distant galaxies would evolve and fast forward. Stars would burn out in minutes. Civilizations would rise and fall in flashes. What feels like seconds to the astronaut could be years, or centuries, for an outside observer. This is gravitational time dilation at its most dramatic, a gravastar as a time dilation engine. Now consider what this means in reverse. Suppose you, standing on Earth, look at an object falling toward a gravastar. You would never actually see it touch the surface. Much like with a black hole, the infalling object would appear to slow down, redshift, and freeze just above the shell. This is not because it has hit an event horizon, but because the time near the shell is flowing so slowly that, from your vantage point, its motion becomes imperceptible. The object continues to move in its own proper time, but your ability to witness that motion is limited by the warping of space-time itself. What distinguishes this from a black hole is that the surface still exists. There is no horizon, no irreversible boundary. In principle, if the object were to bounce or reflect off the gravastar's shell, light from that rebound could eventually escape, albeit delayed, redshifted, and stretched across vast intervals of time. In a black hole, such light would never be seen. In a gravastar, it might return, but only after a cosmic pause so long that human patience and instruments might not endure to see it. This time dilation also raises curious questions about information retrieval. If signals from near the shell take an enormous amount of time to escape due to the gravitational redshift, it might explain why gravastars seem as dark as black holes. They don't trap light permanently, but they delay its escape so drastically that, for all practical purposes, they may appear equally black. This adds yet another layer to the idea that gravastars could masquerade as black holes without violating physics. But the exotic internal structure of gravastars complicates this picture further. Inside the shell lies a core dominated by vacuum energy, a region with negative pressure, behaving like dark energy. The geometry inside such a core is not like normal space. It may be described by a de Sitter spacetime, where expansion and repulsion dominate over collapse and compression. In such a region, time could behave in radically different ways, flowing faster, slower, or even in irregular pulses depending on the model. Some versions suggest the interior may be timeless in the usual sense, an inert, stable bubble of space-time where change is frozen, or where time evolves differently from the exterior universe. And yet, despite this radical core, the interface between the inner vacuum and the outer shell acts as a membrane, connecting two vastly different regimes of space-time. Time at the shell is determined by this balance: outward pull from vacuum energy, inward push from gravity, and the quantum properties of the shell itself. If the shell is dynamic, time near it may fluctuate. If it is static and stable, then the time dilation may be smooth and predictable, but extreme. The implications go beyond theoretical musings. Time dilation affects not only clocks, but radiation signatures, particle decay rates, and signal timings. If we ever detect a compact object with anomalously long signal delays, ultra-redshifted emissions, or unexpected echo timings, it might be evidence not of a black hole's event horizon, but of a gravastar's surface, wrapped in slow time like a cosmic cocoon. One final thought: gravastars may offer a bizarre form of time travel to the future. For any traveler able to reach their vicinity and hover near the surface, the flow of time outside would accelerate dramatically. A few hours spent just above the shell could correspond to millennia in the rest of the universe. If we ever mastered the physics of propulsion and radiation shielding required to survive such an encounter, gravastars could become windows into the far future, a way to leap across centuries by standing still in space. Gravastars show us that time is not merely relative, it is malleable, distortable, and profoundly sensitive to the shape of space-time. And nowhere is this more dramatically demonstrated than near the edge of one of the most mysterious objects ever proposed. The universe ticks forward, but gravastars remind us, not all clocks beat the same. At the core of general relativity lies a set of equations that describe how mass and energy shape the very fabric of spacetime. These are Einstein's field equations, and they essentially state that the geometry of spacetime, how it curves and warps, is directly determined by the matter and energy it contains. For ordinary stars, these equations predict stable configurations like white dwarfs or neutron stars. For extremely massive objects, they predict the formation of black holes, with an event horizon and a central singularity. But gravastars challenge that outcome by proposing a radically different structure, and to make such an object mathematically viable, physicists have had to reinterpret how these equations apply under extreme and exotic conditions. To describe a gravastar, the standard field equations are not thrown away, but rather adapted. The equations themselves remain the same in form, relating space-time curvature to energy and pressure, but the type of matter and energy used in the model changes dramatically. Instead of conventional matter like gas or plasma, gravastars are modeled using two exotic components: a repulsive vacuum energy in the interior, and a thin shell of exotic matter with unusual pressure characteristics. The interior of a gravastar is theorized to be a region filled with vacuum energy, which behaves like dark energy. In terms of the mathematics, this means the energy density is constant throughout the core, but the pressure is negative, equal in magnitude but opposite in sign to the energy density. This combination causes spacetime to expand or repel rather than collapse. When this form of energy is plugged into the stress-energy side of Einstein's equations, the resulting geometry inside the gravastar resembles what's known as de Sitter space, a solution that is smooth, horizonless, and free from singularities. Outside the gravastar, however, the solution needs to match what we observe in the universe. This means that the spacetime outside must resemble the geometry of a black hole. For a non-rotating gravastar, this external geometry is described by what's called Schwarzschild space, a vacuum solution where spacetime curves in precisely the way expected from a black hole's mass. Crucially, this outer solution is indistinguishable from a traditional black hole, as it produces the same gravitational effects on nearby matter and light. The trick is in how these two radically different geometries, the de Sitter interior and the Schwarzschild exterior, are sewn together. This requires a mathematical transition zone, which is where the thin shell of exotic matter comes in. In this shell, the pressure and energy density don't follow the rules of ordinary matter. Instead, they are anomalous, possibly involving anisotropic stresses, where the pressure differs depending on direction. This allows the shell to sustain itself under the immense gravitational compression from outside and the vacuum repulsion from inside. Mathematically, this shell region is described using a technique called junction conditions, which are a formal way of connecting two different spacetime solutions. These conditions are derived from Einstein's equations and ensure that there are no discontinuities or physical impossibilities at the boundary between the inner and outer regions. The stress-energy tensor in the shell is carefully defined so that all quantities, like curvature, mass, and energy flow remain consistent across the entire structure. This complex construction results in a model where the interior resists collapse due to vacuum energy. The shell provides mechanical support using exotic pressure. The exterior looks like a black hole to any distant observer. In short, Einstein's equations aren't abandoned to create a gravastar. They are obeyed, rigorously, but applied in a far more creative and layered way than in traditional astrophysical models. The result is a theoretical object that avoids singularities, lacks a true event horizon, and offers a coherent, if speculative, alternative to the black hole, one where the laws of gravity are not broken, but reimagined. While gravastars present a tantalizing alternative to black holes, offering a solution to singularities, a potential fix to the information paradox, and a new realm of exotic physics, the scientific community does not universally embrace them. In fact, there are many physicists and astrophysicists who remain deeply skeptical of the gravastar hypothesis, and for good reason. Despite their mathematical elegance and conceptual appeal, gravastars face a number of significant criticisms that challenge their viability, both as physical entities and as explanatory models for observed cosmic phenomena. One of the most persistent and fundamental criticisms is the complete lack of direct observational evidence. Although gravastars are engineered to be observationally similar to black holes, and their external gravitational fields are nearly identical, this similarity becomes a double-edged sword. If we can't distinguish them from black holes with any current instrument, then how can we ever be sure they exist? The models suggest that gravastars might emit echoes or delay signals in subtle ways, or possess slightly different gravitational wave signatures during mergers, but to date, no unambiguous observation has confirmed any of these differences. Most of what we believe to be black holes behave exactly as Einstein's theory predicts, without requiring any exotic alternatives. Another major criticism lies in the extreme theoretical complexity and speculative nature of gravastars. To construct one, physicists must invoke not just one, but several layers of hypothetical physics, a de Sitter vacuum core dominated by dark energy, a paper-thin shell of exotic matter with negative pressure or anisotropic stress, and precise mathematical junctions between these regions. Each of these components, on its own, is not currently supported by empirical data. For example, exotic matter with negative pressure has never been observed or created in a laboratory. Its theoretical properties are derived from extrapolations in quantum field theory and general relativity, not from real-world experiments. Critics argue that invoking such speculative forms of matter just to avoid the black hole's singularity may be adding unnecessary complexity to an already working model. In contrast, black holes, while they have their own paradoxes, are supported by a wealth of observational data. We've observed the gravitational pull of stellar mass black holes in binary systems. We've tracked the motions of stars near the supermassive object at the Milky Way's center. We've imaged the shadows of black holes using the Event Horizon Telescope. We've detected dozens of black hole mergers through gravitational waves. In every case, the results fit the predictions of general relativity with remarkable precision. Gravastars, on the other hand, have no confirmed signature, no image, and no direct or indirect evidence to suggest they've ever been formed in nature. Critics also argue that gravastars may suffer from dynamical instability. While some models show that a gravastar configuration can theoretically exist in a stable state, other studies suggest that such objects may be prone to collapse or may not survive perturbations, such as interactions with infalling matter or external tidal forces. If the shell is too thin or the balance between the vacuum energy and the shell pressure is not perfect, the whole structure could destabilize. This instability could cause the object to collapse into a true black hole or to explode outward. The fact that maintaining the gravastar structure may require fine-tuning or special initial conditions leads many physicists to view them as theoretically fragile or unrealistic in natural astrophysical environments. Furthermore, there are concerns about formation mechanisms. While gravastars are proposed to form from collapsing stars, just like black holes, there is no detailed, well-accepted model for how a stellar core, under immense gravitational pressure, would naturally transition into a vacuum energy core surrounded by a thin shell of exotic matter. The standard picture of gravitational collapse doesn't naturally produce this configuration. To make a gravistar instead of a black hole would require unknown physics kicking in at exactly the right time, with finely tuned dynamics that have not been observed in simulations or supported by cosmic surveys. Another line of criticism comes from the philosophy of science. Some argue that gravastars may be an example of speculative overreach, creating increasingly complex theoretical constructs not because the data demands them, but because they resolve theoretical discomforts like singularities or information loss. In this view, gravastars might be elegant mathematical ideas with no grounding in the actual behavior of the universe. If the data fits black holes and black holes alone, then constructing an elaborate alternative without strong observational motivation may be an exercise in theoretical indulgence rather than scientific necessity. Lastly, gravastars, while avoiding the problem of singularities and the information paradox, may introduce new unsolved questions. For instance, how exactly does the exotic matter shell form? Can a vacuum energy core coexist with such a shell under all physical conditions? How do we reconcile the absence of Hawking radiation with the thermodynamic properties of the object? Do gravastars fit into the broader framework of quantum gravity, or do they require yet another patch of speculative physics? In some respects, gravastars may just be moving the goalposts of mystery, shifting the problem from one unsolved region to another, without offering a clearer picture of what's really going on at the edge of gravitational collapse. In summary, the skepticism surrounding gravastars is not rooted in stubbornness, but in a commitment to scientific rigor. While the gravistar concept is rich with theoretical intrigue, its lack of direct evidence, reliance on speculative forms of matter, questionable stability, and unclear formation mechanisms make it a hard sell for many in the scientific community. For now, black holes remain the reigning explanation for what we see in the universe, not because they're perfect, but because they're the best supported by the evidence. Gravastars, for all their fascinating potential, remain ghostly possibilities, lurking in the shadows of theory, waiting for the universe to confirm or deny their existence. If gravastars do exist, the question is no longer just philosophical, it becomes experimental. Can we test for them? Can we tell, definitively, whether the objects we currently call black holes are actually gravastars in disguise? And if so, what kind of observations would confirm their existence, or at least distinguish them from their more traditional gravitational counterparts? This is where the frontier of modern astrophysics meets the ambition of next-generation observatories. Because while gravastars are specifically designed to mimic black holes in almost every detectable way, they also make predictions, subtle, fragile, but measurable predictions, that deviate from what general relativity tells us about black holes. The challenge is not only to look, but to listen to the universe with instruments sensitive enough to catch these differences. Among the most promising tools on the horizon is the Laser Interferometer Space Antenna, or LISA. Set to launch in the 2030s, LISA is a space-based gravitational wave observatory designed to detect low-frequency gravitational waves. Waves that are too long to be captured by ground-based detectors like LIGO and Virgo. These low-frequency waves are produced by massive events involving supermassive black holes, or their hypothetical gravistar twins. Because of its enormous arm length, LISA will be able to capture much finer detail in the ring-down phase of mergers, where echoes, deviations, or secondary oscillations might appear if the remnant object has a surface or a hollow interior, like a gravistar. One of the most compelling ideas associated with gravistar testability involves the detection of gravitational wave echoes, subtle, repeating signatures that could follow the initial gravitational wave burst from a compact object merger. These echoes would be extremely faint, and might occur seconds or milliseconds after the main signal, depending on the size and structure of the gravistar. LISA, with its unparalleled sensitivity and coverage, could be the first instrument capable of verifying whether these echoes are real or just noise. While LISA will be listening to spacetime from space, back on Earth, upgrades to the Event Horizon Telescope, EHT, and the construction of even more precise Very Long Baseline Interferometry, VLBI, networks will give us better visual resolution of compact objects. EHT famously delivered the first image of a black hole's shadow in 2019, an achievement that visually confirmed general relativity's predictions about event horizons and photon orbits. But that image, as groundbreaking as it was, lacked the resolution to distinguish between a true event horizon and a sharply defined surface just outside it. Future enhancements to the EHT, as well as new instruments like the next-generation EHT, are expected to improve angular resolution dramatically. This could allow astronomers to spot small discrepancies in the brightness or size of shadows cast by compact objects. If the object is a gravastar, and it has a surface that reflects or absorbs radiation differently than an event horizon, the shadow might show slight deviations in shape or intensity. Some models predict that a gravastar's surface could produce faint hotspots from infalling matter, or delayed thermal echoes, where light reflects off the shell instead of disappearing forever. Another area of potential is X-ray astronomy. Missions like Athena, Advanced Telescope for High-Energy Astrophysics, and XRISM, X-ray Imaging and Spectroscopy mission, aim to study the high-energy environments around black hole candidates. Gravastars, if they exist, might interact with infalling material differently, perhaps producing anomalous X-ray spectra, or unusual variability patterns in accretion disks. For example, matter falling onto a gravastar could momentarily pile up or bounce back before settling, resulting in emissions not predicted by black hole accretion models. Additionally, precision measurements of pulsar timing arrays could provide clues. Pulsars, rapidly rotating neutron stars that emit beams of radio waves, can serve as cosmic clocks. Their signals arrive with regular precision, and gravitational waves passing between Earth and the pulsar can slightly alter the timing of those pulses. Networks like the North American Nanohertz Observatory for Gravitational Waves, NANOGRAV, and the European Pulsar Timing Array, EPTA, are starting to detect background gravitational waves, and one day might detect the ripple signatures from individual supermassive object mergers. If those ripples differ from expected black hole waveforms in timing, shape, or frequency, it might suggest the presence of a gravastar. There is also the fascinating prospect of using multi-messenger astronomy, which combines different forms of cosmic data, light, gravitational waves, neutrinos, and potentially other particles, to study the same event. If a merger produces gravitational waves but no accompanying electromagnetic signal when one is expected, it might suggest a truly horizonless object with an energy-trapping shell. Or if there is a weak but delayed electromagnetic flare, possibly a sign of matter bouncing off a solid shell rather than falling into a singularity, it might point to a gravastar. With more of these observations happening in real time, the chances of catching anomalies increase dramatically. In the coming decades, the combination of these instruments will create a kind of multisensory astrophysical toolkit, capable of detecting faint whispers in spacetime, subtle flickers of light, or long-delayed gravitational reverberations. These are the tests gravastars have been waiting for. And yet, even with all these tools, the fundamental problem remains. The line between a gravastar and a black hole may be so thin, so imperceptibly narrow, that it could take years, or even centuries, of observations to prove a distinction. But that's the nature of frontier science. We don't always begin with a clear picture. Sometimes we start with a shadow, a ripple, or a strange silence where sound should be. Gravastars are not untestable. They are just exceptionally hard to test. But if we do find one, if a ring-down echo is confirmed, or a shadow turns out not quite as dark as it should be, then the implications will be enormous. We will have shown that the universe allows alternatives to the most feared and fascinating object in modern physics. We will have seen not just the warping of space and time, but a new geometry of reality itself, one that has always been hiding in plain sight. If gravastars are real, they may not only replace black holes in some corners of astrophysics, they might also illuminate one of the greatest unsolved mysteries in all of cosmology: dark energy. This mysterious force, responsible for the accelerated expansion of the universe, remains one of the most perplexing discoveries in modern science. Despite accounting for nearly 70% of the universe's total energy content, we still don't know what dark energy actually is. Yet gravastars, with their core of vacuum energy and their rejection of singularities, may offer a small, strange window into its nature, suggesting that the same repulsive force pushing galaxies apart may also be shaping the most compact objects in the cosmos. At the center of a gravastar lies what physicists call a de Sitter space, a region of spacetime where the energy density is constant, and the pressure is strongly negative. This isn't just a mathematical convenience. It's functionally identical to the behavior attributed to dark energy in cosmological models. Dark energy causes the large-scale structure of the universe to stretch and expand at an accelerating pace. In gravastars, the same kind of vacuum energy is theorized to resist gravitational collapse at a local scale. Instead of letting a massive star implode into a singularity, the vacuum pressure pushes outward, halting the collapse and stabilizing the core into a hollow, repulsive bubble of spacetime. This is more than a structural curiosity. It's a profound conceptual bridge between the smallest and largest scales in the universe. The same physics that governs the accelerating expansion of cosmic voids may also play a role in the internal structure of gravastars. It suggests that dark energy might not just be a force acting across billions of light years. It could also condense into highly compact configurations under the right conditions. In this view, gravastars become local embodiments of a cosmic phenomenon, microcosmic versions of the same expansionary energy that drives the evolution of the universe itself. This connection raises bold questions. Could dark energy, typically treated as a smooth and uniform field, clump or localize under extreme conditions? Might vacuum energy have different phases or behaviors, one for cosmological inflation, one for the current acceleration of the universe, and another for the formation of compact objects like gravastars? If so, gravastars might offer a way to study dark energy in a far more concentrated and controllable setting, at least theoretically. It also forces a reevaluation of how we understand energy density and pressure in the context of spacetime geometry. The stress-energy tensor, the mathematical structure that feeds into Einstein's equations, treats vacuum energy and dark energy as sources of curvature. But unlike normal matter, which pulls spacetime inward, vacuum energy pushes outward, acting as a kind of anti-gravity. This reversal of gravitational behavior is key to both cosmic expansion and gravastar stability. It's not that gravastars defy gravity, they obey it in an exotic way, by exploiting this peculiar pressure-energy relationship. In essence, gravity still curves spacetime, but in the opposite direction. This flips traditional thinking about gravitational collapse on its head. In a black hole, the pressure and density increase until a singularity forms, a point of infinite curvature. But in a gravastar, the repulsion of the vacuum energy becomes strong enough to counteract that collapse, preventing the formation of a singularity altogether. It creates a kind of cosmic stalemate. Gravity wants to compress, but dark energy refuses. The result is a shell of matter squeezed between two radically different spacetime regimes, the outer universe and the dark energy-filled interior. There's also a deeper implication. If gravastars exist, they hint that the laws of gravity and quantum fields might conspire more often than we think to avoid singularities, preferring smooth, repulsive cores to infinite densities. This would suggest that dark energy, far from being just a mysterious, passive background field, could play an active role in structure formation under the most extreme conditions. Some cosmologists have even speculated that if vacuum energy can behave in such a localized way inside gravastars, it might do so elsewhere. There could be primordial gravastars, formed not from dying stars, but from vacuum fluctuations in the early universe. These objects might still exist today, drifting undetected across the cosmos, appearing to us as rogue black holes or other dark, compact masses. If such structures exist, they could contribute to the dark matter problem, providing mass without emitting light, and once again blurring the lines between the known and the speculative. The gravastar model also touches on the cosmological constant problem, which is the discrepancy between the observed value of dark energy and the vastly larger value predicted by quantum field theory. If vacuum energy can be shaped, bounded, or confined, like it is in a gravastar's core, then perhaps the cosmological constant isn't a fixed, universal value but a local manifestation of a deeper quantum gravity phenomenon. Gravastars, in this sense, might be not just black hole alternatives, but experimental templates for the behavior of dark energy under extreme curvature. Ultimately, the connection between gravastars and dark energy challenges us to think more holistically about the universe. It suggests that the forces and fields shaping galaxies and driving cosmic expansion may also sculpt the boundaries of compact objects and determine the fate of massive stars. It implies that the divide between cosmology and astrophysics, between the vast and the tiny, is more porous than we imagined. In a universe where dark energy rules the large-scale structure, and possibly shapes the most extreme small-scale objects, gravastars could be the missing link, a strange but compelling bridge between the known and the unknown. And if we can understand how vacuum energy builds a gravastar, perhaps we can begin to understand how it also builds, and sustains, the universe itself. While gravastars are often imagined as enormous, star-sized entities, potential replacements for stellar or supermassive black holes, there's an equally intriguing idea lurking at the smallest edge of the cosmic scale: microgravastars. Could there be tiny versions of these gravitational vacuum stars, perhaps even formed in the earliest moments of the universe, that still exist today, scattered through space as invisible ghosts? The possibility opens an entirely new dimension to the gravastar hypothesis, one that blurs the line between astrophysics and cosmology, between the macro and the quantum, and between speculation and the tantalizing edge of discovery. To understand where microgravastars might come from, we first need to rewind the clock to the very beginning of time, the early universe, mere fractions of a second after the Big Bang. This was a time of extreme density, temperature, and quantum chaos. Vacuum fluctuations were rampant, energy fields surged and collapsed, and space-time itself may have undergone violent phase transitions. It's already been proposed that primordial black holes, tiny black holes formed not from collapsing stars, but directly from energy fluctuations, might have emerged during this epoch. If that's possible, then it's also conceivable that some of these energetic collapses might have halted before forming a true black hole, producing stable, horizonless objects instead. In other words, microgravastars. Unlike their larger counterparts, which require the mass of a star to form, microgravastars could arise purely from quantum energy densities and vacuum fluctuations. These would be incredibly small, possibly even microscopic, but still contain enough mass energy to curve spacetime around them in measurable ways. Their internal structure would mirror that of a large gravastar, a core filled with vacuum energy or dark energy-like pressure, surrounded by a shell of exotic quantum matter, and an exterior region behaving like a standard gravitational field. The result would be a quantum-scale object with general relativistic features, a truly hybrid entity bridging two realms of physics. Now, if such objects did form in the early universe, could they survive? Surprisingly, yes, at least in theory. If the shell of exotic matter was stable enough, and the balance between vacuum pressure and gravitational compression was maintained, a microgravistar could persist indefinitely. It would not evaporate through Hawking radiation like small black holes are expected to, because it lacks a true event horizon. Nor would it collapse inward, because the core's repulsive pressure balances gravity from the outside. In this way, microgravastars could act as long-lived cosmic relics, untouched since the dawn of time. And here's where things get even more interesting. Such objects could be hiding in plain sight. Because they would emit no light and absorb radiation with nearly perfect efficiency, microgravastars would be effectively invisible. They wouldn't accrete matter like black holes, nor produce powerful jets, nor distort their surroundings dramatically, unless you happen to pass very close to one. Their gravitational influence would be tiny, but still real, and could show up in certain sensitive experiments or observations. This leads to one of the most tantalizing speculations in modern physics. Could microgravastars be part of the dark matter? Dark matter makes up roughly 27% of the universe's total energy content, yet we have no idea what it is. We can't see it, touch it, or directly detect it. We know it's there because of how it bends light and influences the motion of galaxies, but its true identity remains elusive. Microgravastars, if abundant enough, could fit the bill perfectly. They would be small, stable, non-luminous, and gravitationally significant. Unlike traditional particles, they wouldn't interact through the weak or electromagnetic forces, and yet they'd clump and cluster like the dark matter we infer from galactic rotation curves. Of course, there are challenges to this idea. For microgravastars to account for all of dark matter, they need to exist in enormous numbers, and their formation mechanisms would need to be both efficient and widespread during the early universe. Moreover, their gravitational signatures would need to match those of known dark matter behaviors across cosmic scales. So far, no direct evidence for such objects has surfaced, though ongoing searches, especially in the form of microlensing surveys, are designed to detect small, compact objects that might reveal themselves by bending light from background stars. Even outside the dark matter debate, microgravastars raise questions about quantum gravity. If such objects exist, they would necessarily involve both general relativistic and quantum mechanical principles operating in tandem. They could serve as natural laboratories for physics at the Planck scale, potentially revealing the granular structure of space-time or the behaviors of exotic quantum fields under curvature. Some theorists have even proposed that the vacuum core of a microgravistar might be a pocket universe, a tiny, isolated domain of spacetime with its own internal clock and geometry, sealed off from the rest of the cosmos. And then there's the truly mind-bending idea: could a gravistar's interior, whether large or microscopic, serve as a quantum information reservoir? If so, these objects might not only avoid information loss, as they lack an event horizon, but might also store quantum states in a way that protects them from decoherence, much like a perfect memory crystal. This has led to speculations about microgravastars being related to quantum computing on a cosmic scale, or even as building blocks of spacetime itself in certain formulations of quantum gravity. While all of this remains firmly theoretical for now, the mere possibility of microgravastars expands the gravistar idea from a rare black hole alternative into a full cosmological phenomenon, a spectrum of sizes and forms ranging from massive, star-sized gravastars to tiny, primordial seeds that might pepper the universe like hidden grains of gravitational dust. They may be too small to see, too quiet to hear. But if they exist, they may be everywhere, cosmic fossils from a time before time, waiting patiently to be understood. If gravastars truly exist, whether as natural phenomena or theoretical constructs waiting to be engineered, their implications go far beyond simply replacing black holes in our cosmic lexicon. They may represent more than an astrophysical curiosity. They may be a kind of ultimate machine, born from the deepest principles of gravity, quantum mechanics, and energy. And if we ever learn how to understand them well enough, or control their properties, the hypothetical applications are nothing short of extraordinary. In the most speculative but compelling visions, gravastars could serve as unimaginably powerful energy sources, interstellar propulsion systems, or even gateways to other regions of spacetime. Let's start with energy. The structure of a gravistar, with a core dominated by vacuum energy and surrounded by a dense, exotic matter shell, creates an immense reservoir of gravitational and quantum potential. That vacuum energy, if it could be tapped, could theoretically yield massive amounts of usable power. It's the same kind of energy hypothesized to fuel cosmic inflation and the universe's expansion. Even a tiny amount of controlled vacuum decay or energy transfer from this core might release energy orders of magnitude beyond any nuclear or chemical process. This idea parallels speculation about dark energy itself. If we could isolate and manipulate regions of space filled with this repulsive force, they could become limitless batteries, silent, stable, and compact. The exotic matter shell, though equally speculative, could also offer wild technological possibilities. Exotic matter, by definition, has properties that break the conventional rules of physics. It may have negative energy density or negative mass, a requirement in many models of traversable wormholes. If we could synthesize or harness such matter in even small quantities, it could revolutionize physics, enabling technologies that manipulate gravity, time, or space-time curvature directly. Imagine materials that repel gravitational fields or bend light in ways not possible with any natural substance. The shell of a gravistar might not just contain strange matter, it might be a material science miracle on a cosmic scale. Then there's propulsion. The concept of using gravitational or vacuum energy for thrust is no longer purely science fiction. In a theoretical framework where you can extract or manipulate the energy differentials around a gravastar, you might build gravitational engines, systems that fall into artificial potential wells or use space-time curvature to generate acceleration. These ideas are adjacent to warp drives, like the Alcubierre drive, which proposes bending space around a vessel to allow faster-than-light movement without violating relativity. If a gravastar's interior spacetime behaves like de Sitter space, expanding in all directions with negative pressure, then perhaps miniature gravistar-like configurations could be used to create local bubbles of expansion, pushing a spacecraft forward while spacetime itself does the work. Even more extraordinary is the idea that gravastars might be natural or artificial wormhole anchors. In some speculative models, gravastars could be linked to other exotic spacetime geometries, like wormholes or Einstein-Rosen bridges. Their unique structure, lacking a singularity and an event horizon, may allow them to stabilize regions of high curvature without collapsing. This has led to theories suggesting that the interior of a gravastar could be a gateway, either to another region of space-time, or even another universe altogether. While still purely hypothetical, the structural similarity between some wormhole solutions and gravastar interiors suggests that if one is possible, the other might be as well. Taking this one step further, some theorists have floated the idea of artificially engineered gravastars, technological constructs made by extremely advanced civilizations. In this context, a gravastar wouldn't be a natural end point of stellar collapse, but a carefully built device. Imagine a civilization capable of manipulating gravity, quantum fields, and exotic matter at will. Instead of letting stars die into black holes, they might upgrade them into stable, usable gravastars for power generation, defense, data storage, or transportation across spacetime. In the context of the Kardashev scale, such a civilization would be at least Type 2 or Type 3, harnessing the energy of entire stars or galaxies. Gravastars could be their version of a fusion reactor, a computer server, or a wormhole station. There's also the speculative notion of quantum information processing within gravastars. Since they lack a traditional event horizon and might avoid information loss, their internal vacuum structure could potentially store or process quantum states. This opens the door to the gravastar as a kind of cosmic quantum computer, immune to many of the limitations of decoherence that plague earthly quantum systems. Perhaps these objects, especially in their micro versions, could one day be harnessed for post-classical computing, where the manipulation of spacetime itself is integral to the calculation. Even more provocatively, some have asked whether gravastars, or gravastar-like regions, could have played a role in the early architecture of the universe. Could the vacuum shells around such objects have seeded inflation? Could primordial gravastars act as cosmic seeds, shaping galaxy formation or serving as markers of dimensional boundaries? If so, then understanding their physics could unlock clues to the very blueprint of the cosmos. Of course, all of this is speculative, highly so. We have no confirmed observation of a gravastar, let alone the technology to create or interact with one. But science often begins in speculation. It was once fantasy to think of manipulating atoms, flying into space, or peering billions of years into the past with a telescope. The notion of using gravastars for energy, propulsion, or information storage may seem fantastical today, but if these objects turn out to be real, then they may one day become central to the next era of physics and technology. In that light, gravastars aren't just cosmic alternatives to black holes. They are machines, waiting to be understood. They are the stuff of future engineering, of a kind that blends quantum theory, general relativity, and imagination into a unified architecture that could reshape everything from energy to exploration. Gravastars sit at one of the most fascinating, dangerous, and awe-inspiring crossroads in science, the boundary between what we know and what we can only imagine. They are not merely theoretical alternatives to black holes, they are conceptual monuments to the unfinished business of physics, signaling our incomplete understanding of gravity, quantum mechanics, energy, spacetime, and the very structure of reality. When we talk about gravastars, we are really talking about the edge of physics, where equations strain under pressure, where theories stretch into speculation, and where the known universe begins to dissolve into mystery. To begin with, gravastars challenge the foundational assumptions of general relativity. Einstein's theory has proven remarkably successful at describing the macroscopic universe, from planetary motion to the bending of light near stars, from the expansion of the cosmos to the predictions of gravitational waves. But it begins to break down when confronted with the singularity, the infinitely dense points supposedly found at the center of black holes. Singularities are not just mathematical curiosities. They represent a complete failure of the theory. In this regard, gravastars are not just alternative objects, they're rebuttals to the idea that nature permits such infinities at all. Instead of letting a collapsing star fall inward forever, creating a point where all known physics ceases to function, the gravastar model halts this collapse with vacuum energy and exotic matter. It says, maybe gravity doesn't lead to an abyss, but instead to a hollow, stable chamber of repulsive spacetime. This isn't just a tweak to general relativity, it's a signal that a deeper theory must exist, one that can describe strong gravitational fields without infinite curvature, one that connects the quantum and the cosmic. And that's where quantum mechanics enters the story. General relativity and quantum theory are famously incompatible, two pillars of modern science that refuse to stand on the same foundation. Gravastars, by their very design, force these two to interact. The core of a gravastar is thought to be filled with something akin to dark energy or vacuum energy, concepts that arise naturally in quantum field theory. Yet, the shell and the spacetime geometry must be handled using Einstein's equations. The result is a model that marries quantum effects with classical gravity, even if that marriage is still theoretical and uneasily balanced. This alone places gravastars on the edge of known physics. They are prototypes of quantum gravity objects, what you get when you begin to mix the smooth fabric of general relativity with the probabilistic, granular behavior of quantum fields. In this way, gravastars could be stepping stones to a unified theory. They may be what black holes really are once we finally understand the full quantum structure of spacetime. They may be the missing link in a chain that connects everything from particle physics to cosmology. But gravastars don't just question singularities. They also touch on the very nature of horizons. The event horizon of a black hole is one of the most iconic, yet paradoxical, features in all of astrophysics. It marks a boundary beyond which nothing can escape, not even light. But it also raises profound puzzles, such as the information paradox. If information cannot escape a black hole, and yet quantum theory says information can never be destroyed, then what happens to matter that falls in? Gravastars answer this by removing the event horizon altogether. Instead of a true one-way membrane, they offer a surface that looks almost identical from afar but functions very differently. This surface could, in theory, store, reflect, or slowly release information. No singularity. No event horizon. No loss of quantum data. In doing so, gravastars provide a possible resolution to the information paradox, not by breaking the rules of physics, but by changing the game entirely. And then, there's the speculative territory. Gravastars lead us directly into theoretical domains we have yet to fully chart. They require exotic matter, substances that may violate known energy conditions. They make use of negative pressure and anisotropic stress, concepts that are mathematically sound but physically unverified. They suggest that spacetime can behave in ways we've never observed, reflecting light, creating echoes, resisting collapse with pure vacuum energy. In this way, gravastars function as thought experiments in extreme physics. They invite us to test the limits of our models, to consider what spacetime could do under the most unusual conditions imaginable. They allow us to build, on paper at least, a class of objects that defy the rules we thought were absolute, not by ignoring them, but by pushing them further than anyone thought possible. And perhaps most fascinatingly, gravastars may not be alone. Their very plausibility opens the door to a zoo of compact, horizonless objects, like boson stars, fuzzballs, and other exotic configurations predicted by string theory, loop quantum gravity, or higher dimensional physics. Gravastars are not just one idea, they are part of a growing theoretical ecosystem, one that is trying to redefine what it means to collapse, what it means to trap light, and what it means to end. That's what makes them so compelling. They are edge cases, not just of stars, but of scientific understanding itself. They ask hard questions about the tools we use, the assumptions we make, and the truths we take for granted. They might not exist. Or they might already be out there, masquerading as black holes. But even if they remain theoretical forever, they have done something profound. They have expanded the map of the possible. At the edge of physics, gravastars burn like a beacon, not in light, but in imagination, calling us to venture further into the darkness and see what new laws might govern the universe just beyond the horizon of our current knowledge. Whether gravastars are real or not, the fact that they even could exist says something remarkable about the human mind, and about the universe we inhabit. Gravastars stretch the limits of our understanding not because they are unquestionably real, but because they are possibly real. And in that sliver of possibility lies an extraordinary power, the power to reimagine how the universe works. Think about it. Gravastars are not just replacements for black holes, they're challenges to the very architecture of physical law. They ask, what if we've misunderstood what happens when gravity wins? What if the most terrifying monsters in the universe, the black holes we thought we knew, are actually hollow, calm, repulsion-powered shells of dark geometry? What if our deepest fears about singularities and the destruction of information are not necessary, but artifacts of an incomplete picture? Every question gravastars raise forces us to confront how little we truly know. They tug at the foundations of general relativity. They pull at the seams of quantum mechanics. They hint that the vacuum of space might not be empty at all, but filled with seething energy and structure waiting to be understood. And they point to something even more profound, that nature may be far stranger, more elegant, and more subtle than any of our classical models predict. But this isn't about abandoning black holes or rewriting all of physics overnight. Gravastars may ultimately be disproven. Observations may never align with their predictions. The mathematics may turn out to be beautiful but disconnected from nature. That's the risk of working at the boundary between theory and reality. Still, even if gravastars are never found, they will have served an essential purpose. They will have made us question what we thought was settled. They will have pushed us to build more sensitive instruments, to listen more closely to gravitational waves, to peer deeper into cosmic shadows, to search for the echoes of something new. They will have opened the door to new models of matter, energy, and geometry, and maybe, along the way, offer new solutions to problems like the information paradox or the nature of dark energy. They will have sharpened our understanding by contrasting it with something bold, strange, and radically different. And that is the soul of science, to propose, to test, to imagine, and to pursue. Not every theory must be correct to be valuable. Some of the most important models in history were not true in the end, but they pointed us to truths we never would have found otherwise. Gravastars belong to that noble lineage. They are cosmic riddles whose very existence, even as hypotheticals, strengthens the foundation of inquiry itself. If one day we find that the black holes we've been watching for a century are, in fact, gravastars in disguise, echoing, glowing, resisting collapse with dark pressure, it will revolutionize our picture of the cosmos. But even if we don't, even if gravastars remain mathematical ghosts, their presence in our equations will have forced us to ask the hardest and most meaningful question in science: what else could be true? So, in the end, the gravastar remains a mystery. A cosmic ghost, a theoretical monument, a beacon at the edge of what we know. But maybe that's the point. Maybe the universe needs these kinds of mysteries, not just to challenge our theories, but to keep our curiosity alive. Because whether it's a singularity or a shell of vacuum energy, a crushing collapse or a hidden chamber of negative pressure, the story is the same: we are still exploring, still imagining, still wondering. And that wonder, that refusal to stop at the event horizon of our understanding, is what drives us forward into the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.